You press it once and then you can talk, and try not to be too far from the.
All right, welcome. Good morning, everyone. We should get started very soon. Just one announcement is at the end of this session at 10 a.m. we're gonna head outside and follow us. We're gonna take a group photo, so don't disappear at the end of the session. Yeah, I see a few more people coming in, but we'll get started in a minute. Okay, now that we are officially 3 minutes late, we can get started. So we're really pleased to have Jiashang Xu, who's going to tell us about kinematic lensing with DESY.
Okay, thank you. It's my great honor to present our novel kinematic lensing methods with DESY here. And this work is done by brilliant people at University of Arizona and also collaborators at JPL. So first of all, weak lensing has been a core probe of the dark energy surveys and for both now and future missions. And like stage 3 weak lensing surveys like KISS, the DES, HSC has derived very powerful constraints on our universe now. And in the future, we will see weak lensing will play a core role in the Euclid, Roman, and Rubin observatories. But one of the core concern of weak lensing method is that we cannot tell the difference between like whether the ellipticity of the galaxies is due to cosmic shear or its intrinsic shape. and they are degenerate. So this would produce an irreducible shape noise of like approximately 0.3 per component. And if you convert it to signal to noise, it's basically 1% signal to noise per galaxy. And this is the motivation that we have to do average among lots of galaxies. And we are seeing a huge increase in the galaxy number density from the stage 3 survey to the next generation weak lensing surveys. And another concern is the systematics of weak lensing surveys, because we want many galaxies, so we have to include the faint one. For those faint galaxies, we cannot measure their observed shape very well because of all the signal to noise and detector issues, the PSF, all those systematics. And also their redshift measurements has more uncertainties. And also like about the intrinsic alignment of those galaxies and baryonic feedback, etc. So kinematic lensing is a new concept, a new weak lensing method. So we know that the largest source of weak lensing shape noise is due to our lack of knowledge of the intrinsic shape of the galaxies. But for these galaxies, with spectroscopic informations, it allows us to constrain the intrinsic ellipticity of these galaxies. And this can reduce the shape noise of the weak lensing like significantly, probably by a factor of 10. So how can we do that? An intuitive picture is like this. So on the left, we have face-on galaxies and it's being sheared, so we see it's elliptical. On the right-hand side, we see an incline, but actually there's no shear. So from the photometry, they are identical. But if we put a long slit along their major axis, for the left one, we're going to see no rotation curve. For the right one, we can see a rotation curve. That's how we can tell the difference, whether the shape is due to cosmic shear or is intrinsic inclination. And this is called kinematic lensing, and people have published many works on these topics. And sorry for those papers that I haven't listed here. And so how do we measure kinematic lensing with DESI? So similar to the DESI peculiar velocity surveys, we put multiple fibers on the galaxies in the center and also on the outskirts. We can measure a difference in their redshift. That's the low side velocity. But actually, because we want many bright, well-resolved these galaxies, we start from BGS and with imaging from the galaxy survey, and there could be also synergies from LSST deep image coverage. In the end, our typical data would look like something like here. We have put multiple fibers in the center and also outskirts of the galaxies. We expect to see some shift in the central wavelengths from those fibers. And here's a cartoon to give you a more intuitive picture of how these methods work. So we have the observed shape of the galaxies in the color map, and the gray contour is our like model. The intrinsic shape of the galaxy can be basically anything, but as we move along the parameter space, their observed shape is identical. They are fully degenerated. But if we include fibers around those galaxies, we can see that as we move along the parameter space, their predicted spectra are going to look to be very different. And by these informations, we can tell, we can break the degeneracies between the cosmic shear and its intrinsic shape. And one of the potential sense cases is probing assay tensions at very low redshift with DESI kinematic lensing. We have seen increasing tensions in S8 from the S8 measured by the CMB measurements, and also between CMB and all those like lower redshift weak lensing survey, and also full shape power spectrum surveys. And the tensions is not that huge, but it's like 2 to 3-ish sigma, depending on which kind of experiment. So if this tension is real, it will likely to be permanent at very low redshift. And standard weak lensing, because the lensing kernel is so broad in redshift, so it's not very sensitive to if there's something hidden in very low redshift. We cannot just pick that behavior out very obviously. So because kinematic lensing has lower shape noise, so it enables very low redshift weak lensing. That cannot be done with traditional weak lensing, because at lower redshift, the signal lensing is also low. So, but we can do that now. So with DESI kinematic lensing, the science idea would be to measure the matter density fluctuations at lower redshift. In this case study, we study a very simple case. We just split the acid between low redshift and high redshift. They are totally independent, and see how we can probe the low redshift sigma 8. So here we define our galaxy sample. So we start from BGS, is BGS-like sample, but we push to fainter scale cut, magnitude cut like R band greater than 22. And we also require deep morphology and half-life radius larger than 1. This is the purple sample, is very high in number density, that is expensive for DASI. We also consider some more realistic sample, like we use BGS bright or faint or BGS bright. They are reduced in number densities and more realistic, but all of them are mostly like below redshift 0.5, mostly around 0.2, something like that. So we have built a forward modeling pipeline to generate mock image and spectrum and estimate the shape noise and account for realistic signal noise and instrument capabilities. And depending on galaxy sample, the shape noise on average varies between like 0.04 to 0.08. And when combined with their number density, the effective shape noise is going to be similar to LSST year 1 level. And our result is, we just show our result here. So here we study the constraining power on low redshift sigma 8 and also the high redshift 1. So for sample 1, which is the most expensive one, we see is constraining power maybe closer to the yellow one, is similar to LSST year 1. And for the more realistic sample 3, the shape noise might be more closer to the green contour. So on the high Z acid is no constraining power, but on the low Z acid is still very powerful comparable to LSST year 1. So here's the summary. So image and galaxy can break. Image and spectrum of these galaxies can break the degeneracies of intrinsic galaxy shape, and it's very powerful. And we try to apply these methods to DASI, and there could be also like very powerful science case that could also benefit for other low Z science ideas like joint analysis with peculiar velocity and also dark matter studies of dwarf galaxies. Okay, thank you.
All right, great, thanks. We have time for 1 or 2 quick questions. So perhaps I'll start. So at what redshift do you run out of spiral galaxies, and how many fibers do you need? So like, is there any advantage of going above redshift 1, for example?
I think we are good with number density of these galaxies. They are more than we can put on fiber on that. So we are limited by the exposure time and also the number of fibers. So far we expect to use like maybe 4,000-ish out of the 5,000 fibers. But more fiber could be better.
And you need at least 4 fibers per galaxy, or how many do you?
We could try to put 2 or 4 with 2, but we need longer exposure time. They are similar in constraining power.
Cool. Thanks. Any other quick questions? And if not, let's thanks speaker again. Join Zoom. Oh, yeah, join.
Open.
So.
Then I can walk.
Okay, great. Next speaker is and it's gonna talk about dark energy. Here, please.
Hi everyone, I'm Men Xianlin from UPenn. So today I'm going to talk about the dark energy tracking modification of the structure growth. So this is simply a phenomenological model try to address the acid tension. So this work is done with Booth Jane and Marco Ravelry. Okay, so I will briefly introduce acid tension. Everyone know that, and then introduce our solution, and also say what can we do with this for the future. So the acid tension is basically the tension between CMB and entropy measurement and the galaxy survey about the matter clustering amplitude. So here I give an example of Planck and DSEA3. So we see basically DS will prefer a lower asset value. So this was confirmed by some other galaxy survey like KITS and HSC. So it's about a 2 to 3 sigma tension between CMB and the galaxy within lambda CDM. So last year, ACT released their CMB lensing result. So basically, CMB lensing is also consistent with CMB primary anisotropy and intention with the galaxy survey. So also about like 2 sigma-ish. So the red contour is the ACT CMB lensing, consistent with Planck. So this is a nice summary plot. We see all the CMB lensing measure a high asset value, and galaxy lensing measure a low value. So if we think about the CMB lensing and the galaxy lensing, both of these are lensing effect. So the only difference is their lensing kernel peak at a different redshift. So here, I can move. Here, the blue contour, blue curve is the CMB lensing. It peak about say redshift 510-ish, and the galaxy lensing peak at say redshift 0.5. So the gap is about 0.7, which coincidence with the dark matter and dark energy equality. So now, if you think about a possible way to resolve this, a very natural way is to think about you want to suppress the density growth in a low redshift here, but keep it same level as lambda CDM in at high redshift here. So a very natural way is you introduce a time-dependent modification to the structure growth and suppress it late time, keep it the same level at early time. And because of this coincidence, you want to tie this modification to the evolution of dark energy density. So there are some similar idea in literature talk about this kind of time-dependent modification to the structure growth. But here we present a simple model which simply parameterize the modification to the matter power spectrum. So you rescale the matter power spectrum with this parameter as function of redshift, and parameterize it to be proportional to dark energy density. So the simplest one is you fix this power parameter to be 1. So that's the simplest model. So you only have one parameter, beta, control the amplitude of the suppression. So to illustrate that, this is the modification to the matter power spectrum. You see it's same as lambda CDM early time, and you suppress it to some level at late time. And the evolution just track the dark energy density evolution. So with this simple one parameter model, we just fit to the CME lensing and galaxy lensing and their cross correlation, and then we'll find. So the lambda CDM value, which is beta equal to 0, is excluded at about 2.9 sigma level. So, and the best fit is you have a chi-square about minus 7.2, which is roughly compatible with this about 3 sigma level exclusion. So you will immediately see there could be a degeneracy between this beta parameter and your sigma 8 value. today, but there are several ways to break down this degeneracy. So, for example, the DS galaxy survey, you have multiple beams. So the source will be, you have several sources. This will, other than the CMB lensing, you have one source from recombination. This will break down the degeneracy, and also some nonlinear effect and the scale dependence, induced time dependence on CMB lensing will also help to break down the degeneracy, but I will not go into the detail because of time limitation. So again, we also tested with the CMB and SOCP. So we also fit to the Planck high LTTTEE and the low E likelihood. But this late time modification will impact CMB and SOCP via mainly two effects. One is the ISW effect, and another is the lensing effect. In principle, you need to carefully model this, but we don't. So instead we just exclude the low T data and use A lens parameter to cover the possible effect there. So in this sense, we find even after you add the Planck likelihood, you still find like 3 sigma level exclusion to lambda CDI point. So I would say this 3 sigma-ish evidence is pretty robust. So now, so far it's just a phenomenological model, but the underlying physical model, what I'm thinking about is there could be some unknown dark matter, dark energy interaction. So if you have this, your dark matter modification, your modification to the dark matter clustering should check the evolution of dark energy. So we just use this phenomenological model to encode this possible unknown interaction. And for sure, there could be some other orange of such modification, for example, modified gravity or some other thing. But for the future, how can we test this? So I would say the higher redshift probe is very important. And also, in principle, you could include some scale dependence. So particularly interesting is, say, for example, DAISY Lyman alpha data. So again, look at this diagram. So far, we just have many data at low redshift and the CMB lensing data, right? But if we can have some data about redshift 1, 2, 3 here, that would be very useful to test or falsify this model. So yeah, I would summarize here and emphasize this model is simple and testable with the coming soon data. Yeah, thank you.
Thank you. All right, we have time for one super quick question. Is any? So your suppression is scale independent, right? In your model. So I guess you make a prediction for what DAISY should measure in the 3D power amplitude 3D power spectrum, for example. So I guess we can test that.
Yes,
soon.
yes.
Cool. Perfect. Any other question? If not, let's thank the speaker again. Cool. And next up, we have Alex Koleski, who's going to tell us about the new method to measure H0.
Okay, great. Yeah, thank you for inviting me, for letting me speak at this really wonderful workshop. And I'm going to talk about some work that I've recently been doing with Will Percival at Waterloo. And we just put 2 papers out on the archive last month if you want to see more of the details. Okay, so the motivation of this work was thinking about whether we can measure H0 without any reference to standard rulers, either the, oh, what's going on?
We go one further and then back.
Huh.
Okay, it works. Maybe. Could the next person otherwise give their talk now, and then we'll just rotate around if that's okay. So stay tuned for Alex's results on H0. It's very exciting.
So, perfect. Right, change of plan. We have temporarily we have Francis Jan, who's going to tell us about new physics, the electron volt scale with large scale structure. Yeah.
Great. Full screen. Let's see if that actually works.
Yeah.
And I can move. Yes, I can move. All right. Yeah, sorry, we were going to come back to you. Anyways, so I wanted to share some thoughts on SpecS5 and new physics at the EV scales. And thanks for the organizers to put me in the last day. So I have a better background and I can comment some of the things I've heard. So please don't be offended. All right, so the point of this was to illustrate how once you're probing the K modes that SpecS5 actually is probing, of course, DESI is doing the same thing, just a bit differently, obviously. I want to kind of highlight this top axis here, which is actually temperature. This is temperature when these Fourier modes enter the horizon or became causal. So this is basically the highest scale where causal physics could affect these modes. And if you look, this is the typical K mode range that large scale structure survey and the mildly nonlinear and two linear regimes are probing. And this is really the 1 EV to 100 EV scale, right? So this is probing when the standard model temperature of the universe was at the EV scale. And if you want the quick shorthand, how you convert from K mode to temperature, I mean, here's some very simple translation here. Now, in the standard model, there's no physics in this regime, essentially. It's what Martin and his collaborator call always the desert, the Lambda CDM desert. And it just happened that, SpecS5, well, large scale structure, tend to probe this energy scale here. And as we will see also in a second, there are ways to actually extend this to a higher energy. So there's, an important window here where technically you can try to probe new physics in a background-free way, in a sense, because the standard model has no There's nothing happening really there. It's not, I mean, don't take this, take this with a grain of salt, but this is more or less what's happening there. Of course, we have problems in cosmology and orbital tension. You heard about other things. They're going to be able to point here. So there might be need for new physics, which you might believe it, we need it or not. And here's a plot that I made especially for this talk. Again, the same thing, but now I'm showing different models or ideas that people have proposed. And almost none of them are actually my work, except for the SRNU and the ETO stuff. But and on this scale, they all look the same. And here, these points I stole from Kyle from his slide and extracted and multiplied them by 10. Otherwise, it was really hard to see. Of course, I mean the kind of precision you can get with next generation is pretty good. Obviously, it's just kind of zooming in a little so we can actually see anything. And of course, this is purely for illustration. I mean, don't take this for granted. Please don't reproduce this plot. Don't take it from my slide. I always get burned with these things. Anyways, but you see here the kind of difference that some of these ideas, including things like EDE or dark energy, tracking neutrinos that David was talking about yesterday, some of the ethos work, some of Martin's model with the neutrinos, how have a very different shape. And the point of the slide is that there's a lot of variety in the kind of matter clustering that you get in new physics model that you might want to have or not to resolve some of the problems in cosmology. Now, obviously, the nice thing about this is that clearly none of these models, I mean, if you would have these kind of error bars, and again, these error bars here have been multiplied by 5, just again to show them so actually you can see something. It's pretty clear that we have some discovery space here, again, to go with what Mark was saying yesterday. Now, when we talk about, and I'm not naive, like I understand that, as far as SPECS5 is concerned, the drivers are early universe, inflationary era cosmology, and late time acceleration. So I'm not, these are the kind of DOE science driver that they kind of wedded to. But because these K modes become causal when the universe is in the EV to 100 EV scales, you do have this kind of sensitivity to this desert there, where you don't expect much in the CDM. So there's a discovery space here from the matter clustering side. And usually, if you look at science books, these effects tend to be folded into the light relic science case, right? But there's clearly from what I was showing you, you have a much broader diversity of shapes of models for matter clustering that are not necessarily described by light relic. So it's just broader, which we keep in mind. And the nice thing about these ideas, where most of the causal physics is at the EV scales or few EV scales, is that typically these things don't change a lot in the late universe. Don't change really the physics in the late universe. So the things you do in your EFTs of large scale structure is essentially unchanged. I mean, it's not exactly, but to a good approximation. So some of these are actually tractable analysis. So this is not just a pie in the sky kind of thing. So you can actually imagine doing these things. And we've been doing some sort of people. Some of you have been doing this, so it's definitely possible. And there's an interesting question that if you do have that kind of physics in that energy range, that's showing in that energy range, and then you're really interested in the primordial, your kind of primary non-Gaussianity or something, if you do have that physics on top, how much that kind of sow confusion in what you think you're doing, especially if you're searching for things like features. All right, so and kind of moving on to my random thoughts. I have no idea how much time I have because we started in the middle of things. But anyway, I'll try to wrap up. So this is my random thought. Okay, and this was kind of triggered by some of the discussion I had with Kyle, but also when Jeff Newman was talking a little bit about that in his talk. So here's a P5 table, which is already out of date, which is very unfortunate. So while I understand that dark matter is not a design driver for something like SPECS5, and of course we did understand that as part of P5, there's a reason why we put like an S in this dark matter column, because I think there's real opportunities to do good dark matter science with something like SPECS5, but that dark matter science case has not been completely fleshed out, and I think that's important work. Now, if you go back to my, this was with the kind of typical large scale structure analysis. If you really start digging on the dark matter small scale structure side, what you're really doing is really extending your sensitivity to this energy range and pushing it more into the tens of keV scale. So it's something that you probably want to do to further probe this desert. A lot of the things you can do with something like SPECS5 on the small scales is very local, things like Milky Way. We heard about stellar streams. I mean, satellites. You can do. There's a bunch of things you can do. I don't have to go into detail here. And we kind of wanted to show this because this is a plot that was in the SNOMAS paper. I made this plot a long time ago. I'm the only one that really know what went into this plot, and I'm a little embarrassed by it, honestly. But this is really for a personal purpose. But the point on what I'm showing this is a lot of work that needs to be done to better understand how these constraints on this kind of self-interaction and cross-section, which if you have kinematics of galaxies, you can imagine you can do versus warm dark matter mass here. Kind of making these kind of forecasts actually robust is something that we haven't really done. And of course, Ethan has been working on this for a long time by now. And if you want to kind of influence what's going on in the spectroscopic kind of realm, I mean, this work needs to happen now. All right. So this was my random thoughts. Beyond the kind of primary inflationary physics and late time acceleration, I think we have great potential in this kind of intermediate regime where it's not like the very early universe at a very late time. And something like SpecX5 is actually very good for that. And if you add the small scale dark matter you can really push your sensitivity to higher energies. And this dark matter science case is definitely going to be challenging. I'm not naive. I mean, I think a lot of people are relatively skeptical of it, and that's good. And I think the onus is on us to really do the hard work to kind of push to see what we can do with this kind of data. All right, let me stop here.
Great questions for Francis Jan.
Pi has a question.
Okay, so a comment and then a question.
Yeah.
And this is what we were talking about on Monday.
Yeah.
So when we've been looking ahead on the dark matter side, we've really been trying to flesh out science requirements that are based on direct observables rather than, say, dark matter models.
Right. But you did mention that, yeah.
So I'm wondering if you think about this urgent need to better flesh out the dark matter science case, how you would see looking forward that balance between having something that's a science case or a science requirement that's really justified by a particular dark matter model versus one that's based on a simple observable that has some astrophysical benefits as well.
Yeah, I mean, in my book, the reason why this was designed with two axes, because this is challenging two different pillars of CDM. On the x-axis, you say, is it cold or not? On the y-axis, you say, is it collisional or not? So this is challenging two key pillars of blended CDM, essentially. So this is in my book, this is a very interesting things that we should focus on because you're really challenging these two pillars. Now, going back to your point about
how does it flow down to like how about true stars?
Yeah, but to some extent, that's
true targets. Yeah.
I mean, here, I assume that you had basically resolved spectroscopy of some of these dwarfs, and you could know their velocity dispersion to some with some threshold, and so there's some assumption that went into this. Now, if you're going to phrase it constrained into very high level things, the problem is that it's hard to communicate that to the particle physicists that tend to be very focused on lab-based, direct detection experiments. So bridging that gap and phrasing this language is something that they can understand. So that's why I think it's a fruitful thing to do. But I do agree that connecting all the way to what you actually observe and these kind of higher level is very important. And you know where to find me. We can type.
Perfect. Right. Let's thank Francis Jan again. Next up, we have Alex.
Okay, much better. Okay, great. Okay, right. So just getting right back into it. So we basically wanted to propose a new way of trying to constrain H0 without any reference to standard rulers, either the standard ruler from the calibrated size of the sound horizon, or the equality scale, so using the turnover in the matter power spectrum. And yeah, so we wanted to answer this question, can we measure H naught without any reference to standard rulers? And it turns out that yes, we can. There is a way that we can do this, and we do this by comparing physical and fractional energy density. So in other words, a little omega energy density and a big omega fractional energy density. And ultimately, this is tied back to the CMB temperature. So we start with constraints on omega BH squared from Big Bang nucleosynthesis calculations and observations of light elements abundances, which gives us the baryon to photon ratio, which allows us to tie the CMB temperature to the baryon abundance omega BH squared. And then on the other side, we have geometric constraints from late time expansion history, marginalizing over the absolute scale, H naught RD, but we still have information on omega m, essentially from comparing ratios of BAO distances at different redshifts, but without knowing anything about their absolute scale. And then to tie these two measurements together in the middle, we get the baryon to matter ratio. And in this work, we're getting it from the size of the BAO feature in the galaxy power spectrum. And so this little schematic here is just showing the difference between this new method and these other H naught measurements from large scale structure. And so the goal here is to basically have model independent constraints on cosmologies that can change the Hubble parameter, like by changing the expansion history around recombination, and sort of more broadly to be able to decompose parameter constraints into their, into sort of different physics affecting different things. And yeah, so like I said, I wanted to just emphasize that this method is complementary to the other, the standard way of getting parameters from BAO and this equality scale standard ruler measurements. Okay, so as a sort of simple proof of principle of this measurement, we wanted to check that the height of the BAO peak is a robust way of measuring the baryon fraction. And so here what we did is we took the fractional peak to trough height, measured that in the linear matter power spectrum for a number of different baryon fractions. And we showed that the observable here is robustly tied back to the baryon fraction in a variety of different cosmologies, both lambda CDM and a cosmology with some early dark energy that's motivated by the Hubble tension. So this is pretty promising. Okay, so how do we actually do this in practice? So we take the linear matter power spectrum that is goes into our galaxy power spectrum modeling, and we split the transfer function that goes into the linear power spectrum into baryon and CDM components, taking the fitting functions from Eisenstein and Hu. And we have a new parameter that is controlling the ratios of these transfer functions. And then, so we take this modified linear power spectrum with an extra parameter, and we put it into both the sort of classic BAO fitting template-based methods where you have an exponentially damped wiggle power spectrum, and the full shape power spectrum, so where you're modifying linear power spectrum that goes into the perturbative equations, so basically adding this gamma b as an extra parameter in the class PT code. And so this, sort of recapping, there are different advantages and disadvantages of these methods. So in particular, the BAO template fits, we can model BAO reconstruction, which is nice because you're getting a sharpened BAO peak and potentially a better constraint on its amplitude. On the other hand, the method is somewhat more empirical and it doesn't have this full set of nonlinear and bias and nuisance parameters. So of course, we test this method on n-body mock. So we show that we can recover our new parameter within the statistical error in the three different ways that we test. So both full shape and then fitting the template method to both the post-recon and pre-reconstruction correlation functions. In addition to tests on n-body simulations with a single cosmology, we also test our pipeline on noiseless theory vectors with a variety of different cosmologies with varying values of H in both lambda CDM and EDE. And here, basically, we're able to recover the parameters to within this gray shaded 1 sigma error band. Okay, and so now we can, I can show you what we do on data. So we constrain the baryon amplitude from BOSS galaxy clustering. We add these up-to-date BBN constraints on omega BH squared from Schoenberg et al. And then we add the BAO distances marginalizing over RD to get omega M. We also get some information from type 1a supernova, again, as uncalibrated standard candles. And we repeat this for these 3 different ways of constraining the baryon, the omega B to omega M, and get consistent values of H. And in fact, the value of H is more sensitive to what we do for omega M, which maybe is not surprising to those of you who have been following the recent DESI results, where things kind of change around depending on which supernova data set you use. And so, yeah, so just to sort of look forward to the future. So this is comparing this H0 constraint to other things. And so the current constraints of this method are rather weak. So we're now limited by the precision at which we can detect the amplitude of the BAO, which is less precise than the left-right shifting. So that omega B to omega M is basically constrained at worse than the 10% level. But as we all know, there's a lot of really exciting data coming online soon. So we're working right now on DESI year 1 constraints. And sort of the end of stage 4 will have considerably better precision than we have now. So right now we're, this is like a plus or minus 5 H0 measurement. Yeah, so this is sort of, the constraining power here is scaling similarly to BAO. So of course, the next generation of spectroscopic surveys are ideal for this measurement. And with this slide, I really want to emphasize the complementarity of different ways of decomposing this measurement, sort of beyond just the Hubble tension bands that I have here. So yeah, that's it.
Great, thanks a lot. Yeah, David.
So what I'm just confused. I would have thought to have seen some big degeneracies with omega B or something there.
So we're using, we're basically compressing that information into this baryon to matter ratio in the power spectrum. But we do have when we do a full shape fit, we do have some degeneracies with cosmological, with like lambda CDM parameters.
Yeah, thanks, Alex. Yeah, great talk. So if you're using the height of the BAO feature, in this method, so for bias tracers, then do I have to worry about, things like a k-squared bias term changing the height of the BAO feature?
Yeah, that's right. So we always have a k-squared bias. So even in our template fits, we added a k-squared bias and marginalized over that.
Okay, yeah. So you marginalize over that,
Yes.
and it's still
Yes.
Okay. Great, thanks.
And maybe to follow up, so is this a pre or post reconstruction BAO, and you have to worry about nonlinear smearing and things like that?
Yeah. No, so we did both pre and post, and we got consistent results, and as well as modeling, the full shape power spectrum with a more motivated set of bias parameters beyond just the k-squared bias.
Cool, thanks. Sure.
Thanks. Can I understand the fact that the uncertainty from the full shape is slightly smaller than the templates, coming from the fact that there is actually extra information than the ratio of the peak heights in the full shape on omega B over omega M, right? Because, if you take the derivative of P with respect to omega B and then with respect to omega M, there is effects, of course, around BAO, but also after the BAO, right?
Yeah. I think that's right.
Okay, in the interest of time, we should move on. So let's thank Alex again. Next up, we have David Parkinson, who's gonna tell us about cosmology from the matter power spectrum peak.
Okay. Thank you. Thank you for giving me the opportunity to speak. My name is David Parkinson. I'm a researcher at the Career Astronomy, the Space Science Institute. This is some work that I've done in collaboration with Benedict Barcalas, now at the University of Lyon, and Eva Maria Muda at the University of Sussex. So I wanted to start by just going back over some stuff that people have already said, but it's important, I think, to remember that there are really only 4 physical quantities that we use in cosmology, which are the distance from the Earth to the Sun, the mass of the Earth, the monopole temperature of the CMB, and the recession velocity of galaxies. And everything else that we measure is either a distortion, a natural number, or a ratio. And so, for example, the physical scale of the BAO is set by the physics of the CMB, the propagation of the sound waves, which then relates to the CMB temperature, as well as to the baryon density. So I'm going to be talking about the turnover, which is the power spectrum peak, which is a physical scale in the matter power spectrum, which is set by the redshift of matter radiation equality, by the epoch in which the density of the 2 fluids was equal. So we could just write this down in terms of some horizon scale at this epoch, or which then relates to our equality scale. So where does this physical scale come from? If we have a fluctuation which enters the horizon at early times, if it enters before matter radiation equality, it is suppressed. So we have fluctuation height on the y-axis and scale on the x-axis. So its amplitude does not grow until we reach the epoch of matter radiation equality, when it starts to grow. So this is a smaller scale fluctuations with respect to the equality scale, K equality, and none of them grow. But then if you have a fluctuation that enters at or after the matter radiation equality epoch, then it just continues to grow as normal. And we can take a ratio of these and we plot the things that we call the transfer functions. So this is a scale which is imprinted in the matter into the power spectrum, but it's imprinted at a much earlier redshift than the BAO scale. So how can we use this for cosmology? We can use it in exactly the same way that we use the BAO. We measure a scale from our power spectrum, and we use this as a standard ruler. But we want to extract it in a completely model-independent way. Rather than having a power spectrum and fitting the entire power spectrum, we really just want to extract this specific number, this K equality number. So we have our equation, our fitting formula, which is basically just a broken quadratic, which has 4 parameters. It has the scale on large scale, sorry, the slope on large scales, the slope on small scales, and then some amplitude and some position of the peak. And we fit our power spectrum to this, and we marginalize over the other parameters, and we then extract out K equality. The BO here is our systematic. We don't want any contamination from the BO, so we use a mode deprojection effect, which basically marginalizes or removes any influence that the BO have here. We're only interested in K equality, and we want to limit the covariance that has with the BO scale. So we've applied this to EBOS data already. Most redshift surveys don't have enough volume to measure this, but we use the EBOS quasars, which are 343,000 quasars from EBOS, using the Reyes measurements and randoms from EBOS DR16 from the FNL measurement. We do not conclusively detect the turnover. So the turnover would correspond to a positive M on one side and a negative N on the other side. Although we have the slope on small scales, we don't have a rising, we don't conclusively at 2 sigma or more detect the rising slope on the large scale side. We do find an inflection point at the expected scale. So if our fiducial turnover is 16.6 times 10 to the minus 3 H per megaparsecs, what we find is about 17.6 times 10 to the minus 3 with relatively small error bars on the position, even if we find it very difficult to measure this large scale slope. So if we assume that this inflection point that we find is in fact the turnover, we could still use that in the position to make some inferences. So we have an alpha parameter in exactly the same way that the BO measures the alpha. And then this now relates only to the total matter density divided by the total relativistic energy density at the relativistic epoch. And so if we just assume the 3 standard neutrino species, we can recover the physical matter density, omega m h squared, which is not omega m, which you normally have from BO analysis. And then we can combine this with uncalibrated rulers, so uncalibrated supernova or uncalibrated BO, which measure omega m. So our green is our turnover contour. And then when we combine that with supernova, we have red, or if we combine that with BO, we have blue, to then recover the Hubble parameter. So the error bars, the mean value is the same roughly, which is not a surprise given that it's basically dictated because the two data sets that we combine with our turnover are roughly consistent. But the error bars are quite large with respect to other measurements of the Hubble parameter. So here's our comparison. So if we take Cepheid plus supernova, we have a very small measurement. If we take CMB plus BO, we also have a very small measurement. Whereas if we take our turnover plus supernova or our turnover plus BO, the error bar is quite large and consistent with both. But it has a different calibrator. It's set by a different physical scale. So what about the future then? So we're already working on this with DESI data. I can't really talk about that yet because obviously, for obvious reasons, but we would expect to have a conclusive measurement of the turnover at 96%. And we could then use this to make inferences in the same way. And then in the future, for things like MSE or MegaMapper, which were the forecasts that went into this paper, we could then significantly improve our constraints for physical matter density and H naught. So here, volume is key. The modes are linear. Redshift makes less of a difference than just pure volume. If we could get something like, so this is the turnover precision in percentage. If we had something like spec S5, then we would almost certainly be down at the 1% level. Okay, so I'm just going to summarize here. The power spectrum turnover provides an alternate standard ruler. With EBOS quasars, we were able to measure something which is probably the turnover. And using that, we were able to make this DV measurement at a redshift of 1.48, which then becomes a direct measurement of the physical matter density. And then in combination with supernova or BO, measure the Hubble parameter. For full DESI, we will have a conclusive measurement of the turnover. We are confident. And then future spectroscopic surveys will improve our accuracy of our measurement. Thank you.
Great, thanks a lot. Questions? Yes, Francisian, and then Noah.
Thanks, great talk. I was a little confused about where the information is coming from. So you have, you're measuring a bunch of angles and redshift in the sky. So when you try to calibrate, what you really measure is theta equality, is the angle, but you have to convert to an actual K equality, and that is anchored on the CMB monopole. So that's really where the information is coming from.
So the monopole CMB temperature gives you the relativistic energy density, and
Yeah.
then you measure the ratio of that with respect to the physical matter density. Yeah.
So the dimensionful scale that enters the problem is the monopole.
Yeah.
And then you can infer H naught from that.
But we're doing this without any reference to any baryon physics, right? It's only set by this earlier.
Yeah, absolutely. Yeah. Great, thanks.
Cool. Noah and then Misha.
Yeah, so I wonder, it seems that it would probably be fairly sensitive to your treatment of the large angular observational systematics. And so I guess I'm wondering, did you play around with those types of weights, like that actual slope on the large end? In my experience, varies pretty significantly depending on your treatment of that. So do you have a sense of how dependent your sensitivity of that turnover is to that treatment of those observational systematics?
Honestly, at the moment, I don't. This is ongoing. I don't have a good feeling for that at the moment.
Thanks, great talk. Yeah, you mentioned, just wanted to make a little comment. You mentioned that the semi-monopole temperature is important to set the scales, but in fact, all scales in cosmology are set by Rydberg. The semi-monopole temperature only tells you what is your age now. All the scales are set by hydrogen physics. So T0, in principle, you can rewrite all the equations in cosmology in such a way that they explicitly never depend on T0. Thanks.
Okay. So then we should. This one last question. Okay.
How sensitive are you with this to beyond standard model physics, like especially number of light species and
yes.
stuff like that?
So if you change the number of light species, you're changing the relativistic energy density, which will change your predicted position of this scale. Yeah, absolutely.
Cool. Perfect. Thanks so much. And we are switching gear a little bit. Last two talks of the day on wide angle corrections and how to deal with sort of the large volumes that stage 5 will get. So we have Joshua first and then Chen. Watch it.
Mm-hmm. Is it visible? Is it this one? Yep. Okay, yeah, thanks guys. So let me tell you a little bit about wide angle effects in full sky surveys. So, as people have been emphasizing very nicely throughout the meeting, then these sort of next generation large scale structure surveys, DESI, Euclid, Sphere X, and maybe Spec S5 are probing larger and larger cosmological volumes, larger and larger angular scales. And with that, of course, comes a lot of new data, which is great for the science, but also challenges for the cosmological modeling and data analysis. And one of those challenges are these observational effects called wide angle effects. So essentially, it's the observation that as you're increasing the, probing larger angular scales, you're becoming sensitive to the curved nature of the sky. And any effects which depend on the individual line of sights to galaxies, like redshift space distortions, need to be accurately modeled in order to model endpoint statistics. So concretely, if you have a survey which covers a small area of the sky, there's an approximation that you can make which simplifies greatly the perturbation theory modeling of endpoint statistics, and that has been made historically, which is this plane parallel approximation, where you basically say that all the line of sights in your galaxy survey to the galaxies are assumed to be parallel. But as Sphere X, for example, have 80% sky coverage, you obviously have galaxy pairs which subtend large angles, and this sort of approximation is no longer valid. So maybe the next best thing that you can do is you can say, okay, maybe I want to measure 2-point statistics. So I will say for all the galaxy pairs in my survey, I will associate a unique line of sight rather than one line of sight for the entire survey. And this is an assumption which is underlying, for example, the Yamamoto estimator. But this is still an approximation to reality. You still lose information relative to the exact case, which is that you have one line of sight per galaxy in your survey. So these are the wide angle effects, and they're important because they're relevant on large scales, and we also want to do measurements on large scales, like of primordial non-Gaussianity, general relativistic effects, and so on. So how to deal with them? So basically in the literature, there's kind of two approaches to deal with them. One is sort of saying, let's quantify corrections to this plane parallel limit as the angular separation grows. And then the other approach is just treating wide angle effects exactly using the right tool. So I'll talk about the first approach in the context of the power spectrum, and then the second approach in the context of the galaxy bispectrum. So this is based on work with my collaborators at Caltech, including Chen and Olivier. And so the basic idea is that we want to quantify deviations from this plane parallel limit as a function of this angular separation, which is growing, angular separation between the galaxies. And the formalism to do this, it's based on papers from Martin and Emanuele from some years back. And the basic picture to have in mind is this one. So you have your telescope, you're observing some pair of galaxies, and the geometry is characterized by a few parameters. So for example, the distance S between the galaxy pair, the distance along the line of sight to the galaxy pair, where the line of sight is defined in according to some convention, D, and then the angle between the separation vector and the line of sight vector. Okay, so if you tell me these pieces of geometrical information, then you fully specify the correlation function. And after you do a multiple decomposition of that correlation function, the multiples can be further expanded in this angular separation S over D, which here we're treating as a small parameter. And great, so you have some power series expansion. So for example, if you have zero angular separation, you only have the 0th order term in this expansion, you retrieve this plane parallel limit, and then the higher order terms are encoding corrections to that, wide angle corrections. Okay, so it's a power series. So in general, you have to worry about the radius of convergence being finite. And indeed, this expansion is only valid if the small parameter is less than 1. But for sphere X, you will, if you're looking at very large scales, you will have a large fraction or all of the galaxy pairs in your survey potentially violating this condition. So if you're interested in scales which are not too large, though, you can still use this expansion for the correlation function. And if you transform to Fourier space, you end up with an expansion for power spectrum multiples, PL of Ks. And this is a recipe then to calculate wide angle effects in the multiples. And we can use it, for example, to assess how important those effects are for measurements of primordial non-Gaussianity with, for example, sphere X. So as a reminder, sphere X is going to probe FNL local with the power spectrum through the scale-dependent bias. And we can account for the scale-dependent bias in this expansion pretty easily. We just need to make sure that we're accounting for the local average effect to avoid divergences due to the bias on large scales. And if you do that, which we do in the paper, we find something like in a low redshift bin of sphere X, something like 0.2 to 0.5, wide angle effects can mimic an FNL local of around 5. So the sigma FNL for sphere X is 1, so that tells you that you really do need to model these effects. They're important systematic for primordial non-Gaussianity measurement. Okay, so you can use the expansion, but then the question is on which regimes can you actually use it? So to answer this rigorously, we compare the expansion to measurements using the Yamamoto estimator on mock log normal galaxy catalogs. And basically what we find is that the following heuristic seems to hold in general, which is that the expansion is inappropriate when you're on scales k, which are less than 2 pi over the distance to the furthest galaxies in your redshift bin. And if you're on scales which are smaller than that, but still in the nonlinear regime, you can use the expansion, and you only need to go to expansion order n of a few in order to get, say, percent level precision on these multiples, percent level agreement with this Yamamoto estimator. Okay, but then we still want to model the wide angle effects on the largest possible scales available to us in a given survey. So how do you do it? The expansion breaks down. So one idea is to work in the so-called spherical Fourier Bessel basis. So I'll explain how the idea is applied in the context of the galaxy bispectrum. So we also want to measure the bispectrum for sphere X. I think it was said yesterday, you improve your FNL local constraint by a factor of 2 or so in the best case if you combine with the power spectrum. And Chen will tell you how this SFB bispectrum is applied in the context of the power spectrum. How this SFB basis is applied for the power spectrum. Okay, so the basic idea is this. So when you're computing PLFKs or other statistics in Fourier space, you're doing endpoint functions of Fourier modes of the galaxy fluctuation field delta G. So those are eigenfunctions of the Laplacian operator in Cartesian coordinates. But as the sky is curved, it's actually a more natural thing to use spherical coordinates, eigenfunctions of the Laplacian in spherical coordinates as your basis functions, and those are spherical Fourier Bessel modes, and so they're given by this formula here. So you have your fluctuation field, you do a spherical harmonic transform, and then in the radial direction, you use spherical Bessel functions as your basis functions. And this is nice because if you compute statistics in this basis, you model wide angle effects exactly. And the reason why is because now you're really accounting for this picture here where you have exactly one line of sight per galaxy in the survey. And then another nice thing is that you disentangle radial and angular systematics if you use this basis. Okay, so for example, you can compute a bispectrum, a 3-point function of these SFB modes, and you will account for the wide angle effects like that. Another alternative is called tomographic spherical harmonics, which people have done in literature, which is just doing the spherical harmonic part of this spherical harmonic transformation here, but in the radial direction, you don't try to be fancy. You just do the standard thing of having redshift bins. One advantage of SFB over this method is that if your redshift bins are too thick, you lose radial information within a given bin. And if they're too thin, you have a complicated data vector. Covariance matrix becomes maybe nearly degenerate, hard to invert. So yeah, so what we did in this paper, which is very technical, so I spare you all the details, is we did for the first time a computation of this SFB bispectrum in some simplified setup, spherically symmetric window, but with some non-trivial effects in there, like primordial non-Gaussianity. If you're into Wigner symbols, 3J, 6J, and even 9J symbols, I encourage you to look at the paper. And we studied some of the basic properties of the bispectrum in that paper. But unfortunately, we're not ready yet to do like an MCMC with this SFB bispectrum because the computation of the signal is very slow. So there's a lot of oscillatory integrals which appear in the computation, triple Bessel integrals like this, and it's hard to efficiently integrate those guys and at the same time be accurate. Okay, so just to conclude, so in terms of next steps, like immediate goals would be doing a Fisher forecast, for example, for sphere X, for FNL local, combining power spectrum and bispectrum, and in both cases, fully accounting for wide angle effects. And if you achieve that, a next step is potentially accounting for other effects which can bias FNL local measurement, like integrated line of sight effects, so general relativistic effects, lensing magnification, integrated Sachs-Wolf, and so on. And there's various other intermediate steps that can maybe get us closer to these goals. But let me stop there, and thanks.
Great talk. Thank you very much. Could you comment a bit about the covariance matrix, how you set that up in this context?
For you, you mean for the SFB bispectrum?
Yeah.
And, I mean, we didn't even compute it. It's like we can't even compute the signal quickly. It's so slow. So.
And what are your thoughts on this?
It's hard. I mean, like computers will get better, and maybe we didn't use all the right optimizations and so on. So.
Quantum computers.
Quantum, no.
It's always young.
Yeah.
Hi. How is the first bin on redshift? How is relevant for your constraint on FNL? Because you are probing actually a very small volume at this redshift slice, so
true,
I do not
true,
expect
yeah.
a very big.
Yeah, true. So I mean, we just took this redshift bin as an illustration, just because the wide angle effects in that.
Yeah, but the wide angle effects there will just disappear when you're using higher redshift density.
Yeah. So it's a compromise between having large wide angle effects and
if you just discard this bin, how it will degrade your constraint on FNL? Do you have an idea of this?
If you sorry?
If you just do not use this redshift slice, how it will reduce your constraint on FNL? Do you have an idea of this?
Yeah, so I mean, I think that the bias will be less, right? But we didn't actually compare with simulations for that bin just because it's a very large volume, like for higher redshift bins, like if like I don't know, 0.6 to 0.8 or something larger volume. So we didn't check how well you can even use this formalism in that bin, but.
Okay, yeah. Great. In the interest of time, we should move on, but we have another talk on wide angle effects, and then we can have a discussion. Yeah, thanks. So next up is Chen, who's going to tell us about non-perturbative methods for wide angles. Thanks.
Hey, hi, everybody. Yeah, it looks like you guys had a great introduction to wide angle. So I will spare you a lot of introductions. Thanks, Joshua, for doing that. So I'd like to talk to you a little bit more about, basically another method of exactly modeling the wide angle effect in the power spectrum. So just first of all, show you a couple of key peoples that were involved in this work that's posted on arXiv recently. So we have Robin Wen, our graduate student at Caltech, really excellent, driving most of the work here, and Henry Gebhardt, our in-house SFB expert, and Olivier Doré, who's supervising all of the SphereX activities. So let's get started. Just to remind you, SphereX is going to be launching in February 2025. We'll have an all-sky map of galaxies in the infrared and looking at getting hundreds of millions of redshifts and very high volume up to redshift of a few. And basically, we have near spec. Some of the samples will be near spec Z, and some are medium accuracy samples will be more like LSST, photo Z, and that reverse ones. So it's really exciting to be able to map a lot of the universe with SphereX. And for us, like Joshua said, there's a really interesting science goal like FNL that everybody's excited about, but also there are challenges. So we're stepping into various areas for the first time. So large scale systematics on very large angular scales, as well as the fact that we are actually halfway between a spec Z survey and photo Z survey. And so when you start using traditional methods that are very proven for spec Z surveys, like multiple expansions, and you start running into ways about how can I actually accurately model my photo Z errors as well. And we have other papers talking about that. But today I do actually want to focus on the key challenge of the large scale modeling. And so as Joshua already introduced, there's the wide angle effects, but goes along with it, there's also GR effects modeling, as well as window function modeling. And the challenge here is that because we need we heard yesterday and earlier today, we need the bispectrum in order to meet our goals of sigma FNL of 0.5. On top of the power spectrum, we actually need to model all of these things in both the signal and the covariance. So that's a very challenging problem. So let me just start with a bit of a recap of the status in the literature about how we're doing those things so far. So for the power spectrum signal, the wide angle part is pretty well taken care of. As you have seen, there's many methods that exist for WA, wide angle plus window function convolution for the power spectrum. There is actually a public code recently released in 2023 by Fogliani et al. Called GAPC, which also has the GR effects in it. And this actually treats the WA effect fully exactly, so no expansions, power series expansion or stuff like that. So one existing public code. I can tell a little bit more later about it, but okay, let's go down the list. For the power spectrum covariance, we have a little bit of problem with window convolution on the very large scales. There's a mistake in the spelling of the author's name. First author name, Whitcar et al. Has released really great paper recently, and Desi is using the methods as well to do window convolved covariance calculations, but some of the approximations at certain points were playing parallel, and so does not fully extrapolate all the way to the larger scales that we care about, say 10 to the minus 3 h/megaparsec. So, and also we don't have GR effects in it, not that we need it right now, but when you go to fully super large scales, these effects are gonna start creeping in and could become important. Okay, so all of that was power spectrum, and now I'll move on to the bispectrum. So for bispectrum signal, we have a perturbative method that exists for WA and GR. There are various groups, for example, Nuri Kohani et al. Has released methods recently to do this. The window function is still a problem. As far as I know, the EBOS, BOS analysis typically assumes some approximation that's explicitly not available for squeeze triangles. So we have a so that's a problem that needs to be solved. And then for covariance, we need large volume simulations. You want to do mock-based covariance. That's not fast enough, and you can't really do that. So we're working on analytic plus simulations together, like a hybrid version, in order to derive the covariance. So today I won't really talk about any of the bispectrum stuff. But this is, I'll focus on the power spectrum, basically the first item, but actually with an eye toward, but this is all with an eye toward going toward the full bispectrum modeling. So a lot of the bispectrum pieces will actually depend on our power spectrum modeling. So that's where we're going toward. But let me focus on the power spectrum work and leave implications for bispectrum for later. Okay, so just a quick recap. There are many ways to do this. You can do this in the correlation function. You can do this. Sorry, power spectrum is loosely used for 2-point. You can do it in the correlation function, tomographic spherical harmonics. We've heard power spectrum multiples. Joshua just talked to you about it. The power series expansions, and then there's the full version of the GAPC code, which is through the correlation function. So I know there are particle physicists in the audience, so don't want to offend you. Just want to clarify that perturbative and non-perturbative are being used as terms super loosely. This is no perturbation theory behind it. We're just talking about power series expansions versus exact modeling. Okay, so now I want to talk to you about a new method, which is also going exactly, so roughly non-perturbatively through the SFB basis that you just heard. This is a new way to do it more exactly. All right, let's do a little bit of motivation before I give you a lot of math. So the SFB, it's great for exact modeling on large scales, large data vector, but not super suitable for going all the way to small scales. Nonlinear modeling is not super mature. And for power spectrum multiples, actually, nonlinear modeling is more mature. We have EFD1 loop, etc. Well-tested Yamamoto estimator code, and it's a pretty efficient compression, in terms of capturing the Kaiser effect on large scales. So wouldn't it be great if we have the best of both worlds? So this is the key that will give us the best of both worlds. It's a mapping between the SFB to the power spectrum multiple basis. This was actually already discovered by Castilla and White in 2017. We did our project and we discovered this and we were super excited, and we went back to look, did anybody else do this? And turns out, to my surprise, but why is it a surprise? There's one line buried in a lot of beautiful, great results in this paper that was this mapping actually. So was already written down many years ago, but super helpful for us actually in terms of bridging the gap between the large scale and small scale modeling. So what's going on here, as you can see on the left-hand side, we have the power spectrum multiples, and on the right-hand side, we have SFB. And here, be careful, I'm not talking about the same SFB that Joshua was talking about. This is actually a slightly fancier version called a generalized SFB, but in principle, captures the same amount of information, just an over-specified basis. So generalized SFB definitions written over there. It looks exactly like the canonical SFB, except that I let the big L and the small l potentially be different. So if I do that, then I can still define a power spectrum, which will reduce to the canonical SFB if A equals to B equals to L. Okay, this is just math and notation and definition. What would be an interesting thing to notice is the upper indices are the radial indices, and the lower indices are the angular indices. So lower, if you look at the first equation, lower the small l is with the YLM, and the bigger L is with the JL. All right. So a little bit of physical intuition about what's going on in this formula. It looks really pretty, but it's also beyond the elegance. It also tells us how the information is lost. So earlier we talked about the various ways that we make approximations in the line of sight, going from Yamamoto estimator to SFB. Yeah, so I guess we can walk through the math a little bit, and then I can summarize for you how it is done. First of all, we can take the monopole example, and you will realize that you can see that the canonical SFB actually has. We reduce the generalized SFB to the canonical SFB, and you have the same K. Okay, what does it mean that the first K and the second K are the same? Well, these are actually the only modes that you have if you're in the homogeneous and isotropic universe. So in the homogeneous and isotropic universe, you don't have RSD, you don't have redshift evolution, and these would be the only modes you have. Let's call them diagonal modes. If they were different, then we will call them off-diagonal modes, okay? Now, the monopole, that's exactly what you expect from the monopole. It's an average over Fourier vector orientation. And then it's also an average over the redshift bin, right? And the fact that it's average over redshift bin, it's the same for all the other higher multiples, just the fact that in your power spectrum analysis, you decided to pick a redshift bin, choose an effective redshift, and so you lose information, on variations over redshift bin. Okay, and now for higher multiples, well, actually, you would expect that now we would have RSD information coming in because now do higher multiples, and these are exactly what we would see. We would expect to have off-diagonal components. So these are definitely brought back in higher multiples. So if you look at the top formula over there, how it happens is that the same K is being kept, but in the generalized SFB, that information is folded into the upper indices A and B. So that's how it's done, by definition of the generalized SFB. So everything is pretty consistent. Yeah. So how is what happened to the information, right? There is two ways in which we have compressed information. One is the averaging over redshift that I have mentioned earlier, which is just coming from you having to choose a redshift bin and a Z effective when you calculate the power spectrum. When the SFB actually would give you the full information about that on the right-hand side, so we've lost that. Two, we have actually compressed the information into PL and on the angular side according to the Lagrange polynomials and knowing that we have mu squared, mu fourth kind of terms. So that is actually a very efficient compression, and all of that is happening in the Wigner's 3Js and the sum over the A and B indices. Okay, so actually this formula sort of tells us how we have compressed or lost our information. Okay, this is great theoretical talk, but it would be nice to have some plots and show whether they're validated. So we look at the same set of log normal simulations that Joshua has talked about, 10,000 of those, and you compare all the multiples up to 4 and you up to 3, and you look at up to 4, and you look at the theory and sim comparisons on the very large scales. They agree so well. So if you remember in Joshua's plot, on the very, very large side, there were 3 panels, but the leftmost side is where the perturbative expansion fails. And this is the full non-perturbative exact version of it, and it's a really, really good agreement, and we were so happy about it. However, a beautiful consequence of that just comes out of this is also you can compute the covariance exactly. So there's a covariance from the log normals, and you can see how the theory and the sim perfectly agrees. Let me get to my summary slide, which is that we can model WA effect windows exactly for the power spectrum multiples. We can now, the beautiful thing is we can use the same estimator on both large and small scales, just one thing throughout the whole scales seamlessly. It's beautiful, and then you can do your covariance much easily. And plus, we can get an exact modeling of the covariance on large scales. All of this going toward bispectrum. There's a similar version you can do in the bispectrum with the mapping that we already wrote down. And so if we can make the SFB bispectrum computation that Joshua is talking about faster, and the idea is to do that could get us at least half the way we need, then there's much more hope for getting the entire bispectrum signal and covariance modeled, because all of that just depend on a power spectrum signal and the bispectrum signal, and that's fully well modeled analytically. So that's why I am, in terms of implications for SpecZ S5 in the future, I guess it's like you're gonna end up measuring a sphere. you're gonna have a lot of depth. You're gonna have a lot of sky. So all of these things will be super useful for you in terms of getting all of the information that you need from your survey. Thanks.
All right, we have time for a couple of quick questions.
Hi, very interesting talk. I'm just curious that have you thought about also adding the line of sight degrees of freedom into your basis expansion? Because you just mentioned that you have the off-diagonal because, for example, you have the RSD coupling. But if you add the line of sight, that probably also help you to restore the rotational invariance.
Sorry, just want to clarify a little bit what you mean by line of sight. So, so here, as you can see in this basis. Oh, hold on. Yeah, so you can see in the basis, any radial line of sight effects are being basically decomposed using the JLs along the line of sight. So the coefficients of the SFB are able to model all of that. And the way it appears is, in terms of line of sight effects, like say RSD, is that it will show up as a correlation between different Ks in the CL up there. sorry, this is not the canonical one, but in the canonical, SFB will appear as the off-diagonal terms. So the effect should be fully modeled, unless I misunderstand there's some other.
Oh, because I was also remembering the previous talk, I was just wondering what's the comparison to, for example, the Sugiyama spaces.
Right. Yeah, so you're talking about like the bispectrum Sugiyama, right. Yeah, so I think there's it's a different expansion. So there they expand with a multiple YLMs or Legendre polynomials. Is that right? I remember. Yeah, so that's a different expansion. That's an expansion on various different angles. I actually don't know how good or how complicated that one gets with the wide angle things. Have to think about that. Yeah.
Okay, interesting. Maybe we can discuss off.
Yeah. That would be great.
Cool.
But that one was, I can see, looking at more angles between triangles. We can talk more later.
Okay, last question by Zoni.
So is there a sense I can take this formalism and go back to the sort of wide like sort of far observer and sort of flat sky? Is there some sort of way to see how this kind of all expression simplifies? Is there some intuition?
Yeah, actually we've been talking about that within the groups a little bit, like in terms of like the limit, the plane parallel limit for SFB. It doesn't make a lot of sense actually, because in terms of like the you basically start with the assumption that you have all of those like different line of sight in the full spherical sky. I think we did try to like work out particular in certain relationships. You can start to do simplifications like, okay, what would it mean for me to assume a similar line of sight? But yeah, yeah, like it's pretty much CLs give you the whole thing by definition. That construction.
Okay, great. Thanks. Let's thank China again. So this is the end of the session. We have coffee outside, but don't disappear and follow the organizers. We're gonna take a photo first. So it's just outside to the left in the big parking lot.
Come on in.
Does it work? Perfect. Yeah.
All right, let's start the session by a talk by Cheng Zhao on multiplex survey telescope overview and current status.
Yeah, thank you. So good morning. Today I'm going to give an overview of a new spectroscopic telescope to be built in China. And this project is called MAST, and it's led by Tsinghua University. So I'm here on behalf of a large team of scientists and engineers from different institutes in China. In the meantime, we have received massive support from our international collaborators. So yeah, this telescope is called MAST, and the background image is actually the MAST site. So this is called the Saishiteng Mountain in Western China. It's kind of a new site. There are a few peaks there, and a number of facilities have already been built there. Reason it didn't work well. Okay. Yes, let me share my screen. Oh, it's okay. There we go. Yeah, sorry. Yeah, a number of facilities are already built there. So it's in Western China. And the MAST telescope will be built in the peak A. The altitude is a bit more than 4,300 meters. Yeah. So these figures shows the infrastructure of MAST, basically including the dome, the telescope, the spectrographs. And here I would like to share some key figures. So the diameter of the main mirror will be 6.5 meters. And we expect a field of view of around 5 square degrees, so optimized for wide field survey. And the idea is to have 20,000 fibers held by robotic fiber positioners. And the wavelength coverage and the spectral resolution are all similar to that of DAISY. We expect the first light to be in the early 2030s. So if you are familiar with MegaMapper, you will find that actually these figures are quite similar to that of MegaMapper. And actually that's our initial idea, that is to build a northern version of MegaMapper. So currently we have already some iterations of the optical design. Basically, we will have a RC design with a secondary mirror of 2.45 meters. And we rely on a large wide field corrector to achieve the 5 square degree field of view. So in that sense, we will have a 1.6 meter lens for the wide field corrector. This is going to be a challenge for us. And in this way, we achieve both the large field of view and good image quality. So on the funding, we have gathered lots of supports from private sponsors, from Tsinghua University and from local governments. Basically, now we have secured the funding for the telescope itself, but we are still seeking for support for spectrographs, for the operating and maintenance. So currently, we have also designed the focal plane. It's basically the modularized fiber positioning system designed by EPFL. This is also quite similar to what David told on Monday for Spec S5 in the US. So this modularized fiber focal plane is based on the 6.2 millimeter fiber positioners. And currently they are being tested at EPFL. And we have also built a 10% size pathfinder of MAST. It's currently inside the university, and we plan to move this prototype or Pathfinder to the MAST site in this year. And for the site itself, it has already been flattened, and we have already built a dim tower there to monitor the observational conditions. So for the scientific goals, initially we have gathered some broad community inputs from a diversity of fields, including cosmology, astrogalactic and galactic science, time domain, solar physics, etc. So currently we are working on the formation of a scientific collaboration, and we hope that we could support an even broader community and to support more interests, like for those of the audience here. So based on the design of the telescope, we will have a large aperture, so 6.5 meter. We will also have a high multiplex ability. So these facilities will enable us to make potential contributions to cosmology and time domain. And for this reason, we have defined currently 3 main science themes of MAST. And on the top, it will be a next generation deep survey and wide survey in cosmology, and doing basically things that people here are interested. And also we want to support also time domain spectroscopy to understand better the dynamic universe. And last but not least, we want to have a flexible and long-term platform to support both the domestic and the international community. So let's start from the cosmology part. So this is basically in line with what Kyle said on Monday for Spec S5. So based on this large aperture, we will for sure go deeper, so probing a large volume. And also with the high multiplex ability, like with the 20,000 fibers, we hope that we expect to maintain this exponential growth of galaxy spectra. So to summarize, we will probe high redshift, that is large volume, and also high density. That means suppressing the short noise of small-scale clustering. So the sense cases, I just leave a few here, and which are already, lots of them are already discussed in this conference. But yeah, this is quite in line with the topic of this meeting. And apart from cosmology, we would also like to support the time domain studies in the spectroscopic domain, including the follow-ups of transients like TDs, like gravitational waves. And in the meantime, we want to conduct some spectroscopic surveys of transients to have a better understanding, again, of the dynamic universe. And lastly, we want to maintain some ability of flexibility to permit potential new discoveries. So for this purpose, we face basically a big technical challenge, which is to the design or the strategy of fiber positioning. So to allow for flexible time domain spectroscopy, basically we need to enable the power of follow-up transients. That means that if we get alerts or announcements of transients, we should be able to add the target in our target list immediately and reconfigure our fiber positioning system. And this is a big challenge because of the high computational costs. So currently we are working on adapting the DASI FiberSim code for the MAST focal plane. We have basically tested 10,000 fibers on this modularized focal plane. But in the end, we find that it's basically too slow to support the real-time reconfiguration of the fibers. So for this reason, we are also developing some AI-based optimization tools for fiber positioning. And hopefully, on success, we will be able to do fast configurations and fast adding of new targets. So for the scientific preparation, currently we are drafting a cosmological white paper, basically list the science cases that can potentially be tackled by this Mars telescope. And the idea is to submit a white paper by the end of the year. And for this purpose, we have basically performed some preliminary target selections based on the HSC data to select high redshift galaxies. And based on the density, based on the bias of these traces, currently we are working on feature forecasts of different cases, like the forecast on F and L. But this work is based on linear theory and just pulse spectrum. And hopefully with this Mars cosmological white paper, we'll do better. And also, members, this is just an example, because members in our team are working on these constraints on warm dark matter from neutral hydrogen distribution. And we've also performed forecasts for Daisy and Mars in this scenario. Yeah, basically we wanted to have more complete forecasts in the end, by the end of the year. So to be honest, to some extent, the US Spec S5 and the Mars are competitors. But I think there is still room of collaborations in science. Say, this, I just list some examples here. For instance, our volume will be complementary, at least for the South telescope of Spec S5. Also, we will be complementary in longitude, so that's optimal for time domain targets. Also, I believe that the cosmological studies for next generation surveys will mostly be systematics limited, because we are almost hitting the cosmic variance limit for many sense cases. And in this case, having two different facilities for cross validations of different systematic issues will be crucial for reliable cosmological constraints. And also, as we have already been benefit from DASI for its public software tools, I believe that the development of the new techniques like the fiber positioning systems, softwares, will benefit for both telescopes. Yeah, so basically, we can do synergies in science. And in this spirit, we are currently working on a scientific collaboration policy. We hope that we could finalize it or announce it by the end of the year, so stay tuned. But the basic idea is that we welcome any form of international collaborations. And also in this spirit, we have basically organized a series of scientific activities quite similar to the spirit of this conference. So basically, we organized a series of talks called We Must Talk, and invite mostly junior researchers who are potential users of MAST or Spec S5. And the speakers include some audience here already. And we hope that we can organize more in the future and gather more broader interests. So that's basically it. So this is going to be a 6.5-meter telescope in the Northern Hemisphere and probing next generation cosmology and time domain science. And here I put a link of the website here. And if you're interested, feel free to visit the website or directly contact us. Yeah, we look forward for comments and suggestions and the potential collaborations. Thank you.
Can you comment more on target selection, both what photometric samples you're using to do target selection and what kind of targets you're using?
So currently, we're mostly focusing on LBG. I think Christoph will talk about this later. This is because our wavelength coverage is just similar to DASI, so optical range, and we will be able to probe the Lambda alpha line between redshift 2 and 4 or something. So that's basically our main target. And also, this is limited by the available imaging surveys. I'm not sure if there are more interesting targets at this ratio range for us in the Northern Hemisphere in the near future. So yeah, LBG is our main target.
sharing this. Yes. All right. Our next speaker is Andrea Fonfilera, talking about running from the Lyman Alpha Forest.
I've been trying to run away from the Lyman Alpha Forest, but still here I am after 15 years. Yes, so I was a bit surprised that in the beginning of this meeting, but also in other similar meetings, there's a lot of talk about measuring B modes. There's a lot of talk about FNL, a lot of talk in this particular meeting about primordial features, but there were not many mentions to running. I think Oliver Philcox mentioned running in one of his slides. And I don't know whether it's theoretically not that appealing anymore, or whether observationally it's hard and it's not clear how well we'll measure running and so on. So I decided to put together some slides. It's not a very well prepared talk, so apologies, about what can we do from the Lyman Alpha Forest in terms of measuring running. So there's this paper from 2016 where we had the forecast of how well we'll measure cosmological parameters from DESI, and in particularly this plot shows how better we will do with respect to Planck plus Bose BAO. And there are different improvements in many cosmological parameters, but I want to focus on this one, running. And there's this potential to let me try to hide my it's a little bit okay. I want to be here, right? So there's this potential of measuring running 3 times better than Planck, to basically 2 times to the -3, and the main contribution to that comes from the Lyman Alpha Forest. So the green is this extra information when you use not only Lyman Alpha Forest BAO, that's included in the other ones, when you also add full shape Lyman Alpha Forest if you want. So this is another way of looking at this. Green is an actual, it's a different type of forecast, but similar. Green is like a Planck chain with free running, and then gray and red shows what happens when you add either BAO or when you add this Lyman Alpha full shape, and blue is when you combine, and it's just a way of saying there are very different degeneracies, so combining both helps a lot. So why is that? It's like a landscape of different probes, as well, always super biased, this type of plots. But DESI will have many galaxies, but also will have this Lyman Alpha Forest that offers a unique redshift range, but also allows you to look at linear modes up to much smaller scales, partially because it's higher redshift, but also partially because it's not as impacted by nonlinearities on very, on very high density regions. We are tracing randomly parts of the universe, and most of our signal comes from mild density fluctuations. So for those who don't know what the Lyman Alpha Forest is, just a very brief intro. This is a simulation by Andrew Ponsen, just showing that as the light travels across the universe, not only the spectrum of the quasar is redshifted, but there are also all these absorption lines that come from neutral hydrogen along the line of sight. And the idea is to take all those observed quasar spectra and use this forest of lines to reconstruct the density of neutral hydrogen between the Earth and those quasars. And already in DESI, we have more than 500,000 of those quasars. That's not DESI. That's someone was complaining in this conference that we should stop using this plot from the 90s, I think. But I love them. So this is on the top panel, you have a low redshift quasar. At the bottom panel, you have a very high redshift quasar. And they are, of course, shown in emitted wavelength. So, emitted rest frame wavelength. So you can see that they're very different. The high redshift one has all this huge number of absorption lines that are not present at low redshift because the universe is basically transparent to Lyman alpha photons. Right, so from every line of sight, from every quasar, we kind of have something like half a gigaparsec of information, and we use that to make 3-dimensional maps. So in this conference, we have also heard a lot about Lyman alpha. Well, not a lot, but there were several talks yesterday talking about Lyman alpha. So I think it's important to make this distinction. A lot of those talks were talking about Lyman alpha 1D power spectrum, so correlations along one line of sight on very small scales. There were also talks in the first talk by Natalie. She showed some DESI BEO results, and one of them came from the Lyman alpha, but in that case, those are very large scales, 3-dimensional informations. So those are two very different types of analysis. And the plots that Natalie showed also included the quasar Lyman alpha cross correlation. So in a way, within the forest, there are these 3 different probes. The 2 on the right, the 3D correlations are often treated together. The 1D correlation are often left separately. So it's important to I would love it if when people talk about Lyman alpha, they specify, like, are we talking about one type of analysis or the other? Because they're very, very different type of analysis, at least to date. So going back to this plot, on large scales, 100 megaparsec scales, we have this 3D analysis, and those measure expansion and geometry, right? They look at 3D correlations on large scales, and we model them with linear theory or maybe perturbation theory, but limited to fairly large scales. while the 1D analysis that we heard about yesterday, those measure clustering or growth. They look at 1D correlations on very small scales, and the modeling is completely based on hydrodynamical simulations and emulators around those hydrodynamical simulations. And this is a difficult topic, also very exciting. So my background is that I've been moving from left to right slowly, and I'm trying to actually get deep into the right 1D correlations, but I keep being dragged to do BA analysis because those are also cool, but they're not as exciting. I think the 1D correlations is all more exciting. Anyway, so the problem here is that the hydro simulations are difficult, and the emulators built around those hydrodynamical simulations, you have to check that different codes agree with each other. You have to test that you're marginalizing over the uncertainties in the thermal history of the IgM, reionization. We heard about reionization yesterday as well. All these kind of things are important. So we had an effort with some of my students at UCL, then at IFAE in Barcelona, to try to build one of those emulators. We call them LACE, the Lyman Alpha Cosmology Emulator. And they're not state-of-the-art simulations. They're small simulations because we are not experts in high-performance computers. So it's more like a proof of concept, right? The idea is to develop all these techniques with these smallish simulations and then apply that to the real simulations. We have some of the experts in the room on real simulations. But what was kind of fun is to play with what is the best possible parameterization that we can use to do these optimal emulators and so on. And one of the things that we did that I thought was very nice was to show that if you parameterize your dependence to cosmology, not with cosmological parameters like omega matter or sigma 8 or omega baryons, but you try to parameterize it as a function of linear power spectrum at the redshift that you're measuring, you then can have like a model-independent emulator. And we showed that indeed we had some test simulators that had different cosmologies than the ones in the training. Some of them had running of the spectral index. Some of them had massive neutrinos. Some of them had curvature. Our training didn't know about any of those parameters, but still, because we were parameterizing things in a model-independent way, we could recover the truth at 1% precision, even for those exotic cosmologies. And I'm showing this because running is one of those that we tested. It was not a very extreme running. It was like less than 2%. Right. So why am I showing this? Is because, well, if you're interested in running, we can measure those things, right? So, we can measure those things from basically because we are measuring the linear power spectrum on very small scales. And if you combine with Planck on very large scales, that's where this factor of 3 that I was mentioning in the beginning comes from, right? So, okay, so one of the things that I really want to do as well is that I mentioned these two very different communities. If you look at the papers from BOS or from EBOS or from DESI, there are different authors working on the 3D analysis and different authors working on the 1D analysis because they are quite different, right? But it would be nice to talk more between the two of us and to slowly bridge the gap between those two communities. And I'm very happy that in the last few years, there have been several efforts to do that. So on one hand, there have been new estimators for pushing these 3D analysis and slowly pushing them to smaller and smaller scales. So we wrote a paper with Pat McDonald and Jess Lozar showing that we can have an estimator that can measure unbiased the power spectrum in 3D, even going to like K of 1 or so. There have been similar independent efforts lately by Abdul Karim in Saclay, Roger here, who is giving a talk right after me, Ben Horowitz also here in Berkeley, of like different new ideas for how to measure 3D correlations and bridge this gap by taking them to smaller and smaller scales. And also in parallel, there have been several efforts to improve the modeling. Sorry, so the top right should actually be with those on the left. So the top right is like full shape analysis that we have already started to do with Andrei Kuchev here in the audience, trying to do full shape beyond BAO on these 3D correlations and measure Alko-Paczynski, redshift space distortions, things like this. And there have been new perturbation theory models by some people here in Berkeley and so also by Ivanov here also in the audience. And we are also working on emulators based on hydro simulations for the 3D power spectrum. So it's great to see all these different new tools appearing because, for instance, these emulators are 3D. And I believe also the EFT work by Ivanov might allow you to model at the same time in a consistent way those small scales and the 1D scales and the 3D scales. So it's great to see that all these things are happening, and hopefully by the time SPECS5 is working, we can do more like a coherent analysis of all the Lyman alpha first information. Right, so I was asked to talk a little bit about what can SPECS5 do for us. And I think what is interesting is that when I was talking about this forecast, I mentioned this factor of 3, the number that we quote in that forecast from DESI, it's still 0.002. And that's a factor of 2 too large of an error bar if you want to hit that floor that we heard on Monday of 1 minus ns squared, right? That's a factor of 2 smaller. So if you want to hit that floor, you need to improve the constraints. So how do we improve those constraints? Well, I think we should be looking for new ideas for how to improve that constraint. And one thing we can do that is, I think, fairly possible is to just have better, more Lyman alpha forest data. And you could imagine that we have already saturating that information, but we're still very far from cosmic variance. So I stole this plot by a paper by Matt McQueen and Martin White from 10 years ago or so. And I modified it a little bit, so not all of the lines are from that paper. With my paint skills, some information like cosmic variance is still, if you look at BOSS, magnitude 22, we're still very far away from cosmic variance. If you go to DESI, we're still far away from cosmic variance, especially at redshift 3 or redshift 4. So, just by going to fainter and fainter magnitude limits, you can have a lot more information, even in the same area and in the same redshift range. However, it gets really expensive to get more quasars because also there are not that many quasars. So it's hard. But what they also show in that paper is that you can also use Lyman break galaxies as background sources. So if you can use the same Lyman break galaxies that everyone in this conference is talking about from the point of view of galaxy clustering, you can also take the same galaxies and look at Lyman alpha forest absorption on those galaxies. It's hard because the continuum, it has different, like the signal to noise is a little bit lower, but people do that. There has been already some papers by Keegan Lee in the Clamato survey, but also by others in the Lattice survey, I think in Southern California, that show that these things can actually work, right? So it would be fun to start looking at what can we do in terms of Lyman alpha forest from the Lyman break galaxies that will be discovered in SPECS5 or maybe already in DESI2. So that's it. So in summary, 3D correlations of the Lyman alpha forest, give us, as of today, the best measurements of BAO and expansion at high redshift, but also small scales 1D correlations can give us this different window to go to small scales in the linear power spectrum, and that's good for neutrino masses, but it's also good for running. And yeah, so we're still cosmic variance limited, so please, we're not cosmic variance limited, so just give us more forest. Thanks.
Questions? So I have a question. So do you then have a prediction for SPECS5? What kind of error on the?
So there are several limitations. One is that we need to make the first exercise as in if you had that many LBGs and that was the signal to noise that we would have, how well we would measure the flux power spectrum. And that's something that we need to work out, but it's hopefully not too much work. The second part is, given that, how well you will constrain cosmology. And for that, you need those emulators. So we now have a working version of the emulator that we circulated with the working group of DESI a couple of weeks ago. And today in this conference, we're sitting with Andre Kuchev and with Julian Guy, saying okay, we really need to make a forecast code, make it public so that every survey can start making those predictions, but we don't have them yet. Hopefully not too far in the future.
Have you thought about? Thank you. Have you thought about higher order statistics with the Lyman alpha forest? That's gotten a lot of mention at this conference. And I know that a few years ago, I think Paul Martini and David Weinberg had a student at Ohio do some preliminary work on a 3-point function of it. Is there any way to, forecast whether that would really help us tighten things to kind of see if it's worth the work of building it?
So I remember, I think 20 years ago, there was a paper, I think it was Rachel Mandelbaum, I think Uroš or Pat or Zaldariaga was also there. And it showed that, yes, if it's like in galaxies, right? You add a 3-point function, you break the genesis between amplitude of linear power and bias or mean flux in this case. Yeah, there's potential, but again, we don't have emulators for that, right? So I do plan in the next year or so to use the same simulations that we have for that to build a first version of the bispectrum emulator. And then it would be easy to fold that into the forecasting tools, but we're not there yet. But yeah, of course, it should definitely help. And there's also other bispectrum. So this particular one that was mentioned 20 years ago was about the 1D bispectrum, right? But you could do other bispectra. So there are people already, we saw a paper, was it yesterday or something like this on the archive about the CMB lensing cross Lyman alpha power spectrum correlations, and that's a bispectrum that would also break those degeneracies to some degree. But in that case, we're even farther away because it's not clear how we would do the emulator.
David? Okay. Yeah, so it's nice to have something with a target. How far away, let's say you had everything figured out, DESI can get to 0.002, is that 1 sigma or 5 sigma?
That was 1 sigma, I think.
Well, okay. So to actually make a measurement, it's quite a bit
Yeah,
further. Yeah. Okay.
If you want a 5 sigma detection of non-zero running, then you need to do a lot more than that. But I also think, well, I really don't know much about inflationary models and what do they predict for running, but I've heard some papers do talk about predictions that are larger, like an order of magnitude larger. Some of the simpler models predict this 10 to the minus 3, others predict a factor of 10 larger than that, and those will be within reach in the next few years. So I don't know, are there models of inflation that produce large running that are somehow motivated? Because I think that would be nice to talk about those things, but
yeah, we can
I
have
no
that
idea about
during
this.
the discussion. Yeah, thanks. Let's thank Andrew again. All right, so our next talk is by Roger de Belsons, talking about cosmology with the Lyman alpha forest.
Hi everyone, I'm Roger, and thanks Andreu for the introduction to the Lyman alpha forest. And today I want to focus on certain aspects that he mentioned today. And basically, the Lyman alpha forest was dreamt up 20 years ago by half the people here in the audience, or some of them. And not much has happened with all those dreams. But in the last few years with eBOS, DESI, we're having now so many lines of sight that we can do a lot of interesting science. And with Spec S5, this become even more exciting. So let me show a slide that is slightly different to the one Andreu showed. So what are the scales that we're actually probing? So on one hand, you have the very large scales, so the 3D information from the correlation function or the power spectrum, where you can get BAO, or also more recently efforts in the full shape, either with compressed statistics or directly inferring cosmology in an EFT sense, as Ivanov has described recently. Then at more intermediate scales, from 10 down to a few megaparsecs, you can measure the amplitude and shape of matter clustering and even the sum of neutrino masses through, for example, cross correlations between the Lyman alpha forest and the CMB. And then at very small scales, you have this very dense sampling along the line of sight of each Lyman alpha forest, where you can measure the so-called power spectrum to also get the neutrino masses, IgM thermal parameters, constrain warm dark matter models, or primordial black holes. So in principle, the Lyman alpha forest gives you a huge range of scales at a quite high redshift. And now the question is, why do we need another high redshift measurement? Now, this is a plot I stole from Andrei, which quite nicely shows going from a dark energy dominated to a dark matter dominated era. Here from very low redshift with a 6-degree survey, then BOS, eBOS, and eventually to the Lyman alpha forest. And you see a quite nice rotation in the omega M H0 RD plane. And the Lyman alpha forest really is helpful in order to break some degeneracies. And what we've been focusing here so far is to pursue 2 different paths to do that. One is what Andrei already mentioned, is measuring the Lyman alpha 3D correlation, and then also the cross correlation with quasars. And this has been done exquisitely in the configuration space, and we've been trying to do the same thing now in Fourier space, so measuring the 3D power spectrum. Something that is a bit awkward with the Lyman alpha forest is the window function, because you have the very sparse sampling transverse to the line of sight and very dense sampling along the line of sight. And what we did here is we just took the public eBOS dataset and try to use the best of both worlds. So taken configuration space pair counting algorithm, and then weight that by an exponential, effectively measuring the Fourier transform. That was something that was whipped up by Oliver and Daniel a few years ago in the context of galaxy power and bispectra. And as we see, it works actually surprisingly well with some caveats in the context of Lyman alpha forest. And the next slide I want to show is how do we compare that to theory in order to extract then cosmology from the Lyman alpha forest? And so far, there have been quite a lot of focus on emulator or simulation-based models. So you take on large scales, roughly Kaiser, and then you apply a nonlinear correction terms that you obtain from hydrosims, and that works very, very well so far. And recently, there was quite a bit of effort to develop new perturbative models that are theoretically very well motivated, however, a bit more difficult to compute on the math basis. But given that we're at quite high redshift, we have a much higher K-reach in contrast to galaxies. So as we saw earlier, here we measure the power spectrum up to K of 0.3 and compare that to a simulation-based power spectrum correction. And as a next step, what we're working at the moment is to see how much can we get out of the Lyman alpha forest in the context of a full shape analysis. So this is a very crowded plot, but the key idea is here you can do quite a lot of things with the Lyman alpha forest. So this is the power spectrum measurement down to K of 1, which is something that we couldn't do in galaxies, but that seems to work in the context of the Lyman alpha forest. And on the left-hand side, you see the plot I showed you earlier, where we could just do the standard full shape information. And once we go to smaller and smaller scales, we can then start constraining IGM thermal parameters, warm dark matter models, and even primordial black holes. But here, our theory prediction starts to break down that we have at the moment. So can we maybe extract more with EFT approaches or different perturbative approaches? And that's what we're exploring so far. Switching gears slightly is the question, how can we break degeneracies with bias? So one way that Andrea mentioned earlier, and that has been done exquisitely in DESI and EBOS, is to not only use Lyman alpha autocorrelation, but also the cross-correlation with quasars. On the other hand, what you can do is also do a CMB cross-Lyman alpha analysis. And the CMB is sensitive to very large scales. So here on the left-hand side of the plot. And then the Lyman alpha forest at quite high redshift, very small scales, you can very nicely measure then the suppression in the power spectrum. And that way you're sensitive in the cross correlation to the amplitude and shape of matter clustering, and you can correlate to very different regimes. Now, talking about breaking bias degeneracy. So here in this plot, I wanted to briefly mention the CME's cross Lyman alpha power spectrum. So the direct correlation of the kappa map, so the CMB lensing, and the Lyman alpha forest flux fluctuations. Andrea was mentioning the squeezed bispectrum, so the P1D that is exquisitely well measured to down to small scales across the CMB. But here we're directly cross-correlating it with the Lyman alpha forest field. One challenge here is how do you extract these long wave length modes along the line of sight? But if you are able to do that, then you can quite nicely break this bias sigma 8 degeneracy from the auto, the cross spectrum, because you have different powers in the bias and have a sweet constraint on sigma 8 hopefully soon. So what we did here is we developed a method in order to extract these long wavelength modes along the line of sight using a PCA-based continuum fitting approach, and we get a 4 sigma-ish detection for the power spectrum. A few caveats about this plot. The error bars are quite huge, as you can still see, and our results depend quite sensitively on the type of continuum fitting that we do. So what we're aiming at the moment is making that much more robust, see how this scales as a function of signal-to-noise ratio, and also include correlations across different lines of sight. So here we're just correlating the CMB that is exactly at that same point as our line of sight of the given Lyman alpha forest quasar. So what happens if you include now an additional power of the Lyman alpha forest, so the squeezed 3-point measurement that Naeem Karasaili was doing within DESI. And here you have a measurement where you basically do a linear response type analysis of the power spectrum to the power spectrum of the Lyman alpha forest along the line of sight of the CMB. And we get a little bit higher detection of roughly 5 sigma of the squeezed bispectrum. So this shows us that there is some signal that we can measure, but there's still a bit of way that we have to do in order to have a solid cosmological interpretation from this, but it seems quite exciting. So coming to the end now, what do we gain from SpecS5? And I think Andrea already said a lot of very relevant things here. And what I would like to add to this is, obviously in an ideal universe, we would like to have infinitely many Lyman alpha skews with infinitely high signal to noise. But as you can see from this plot, so on the left-hand side, you have your 3D flux power spectrum. The noise component that comes to it, also called the aliasing part, is a function of your 1D power spectrum that is very well measured, divided by some effective number density. And that sensitively depends on the noise power spectrum of each individual skewer, which in turn is a function of the signal to noise and the number of sight lines that you can get. So what we would like to have is then more lines of sight. And additionally, we could also add in cross correlations with other high redshift galaxies in order to squeeze more information out of the Lyman alpha forest. So thanks very much. So just to sum up here, Lyman alpha is an interesting topic. We're at high redshift, so we can go to higher K and probe a wide range of scales, and happy to take any questions. Thank you.
So,
So
I have a question. So this emulator versus EFD, can you describe some of the pros and cons of that approach?
So the emulator approach has been shown to work actually surprisingly well, especially also in the P1D approach. What you need if you want to go to very large scales are huge boxes, but there you can get away with linear theory. So actually the hybrid approach of just doing a Kaiser times some nonlinear correction terms seemed to work very, very well. In the EFT approach, that's something kind of was recently developed. We're testing it at the moment. You potentially have a lot of bias parameters that may be very degenerate with each other. So that's something to explore how well that actually works. But you have a very well motivated theoretically description of your one loop power spectrum. So that in principle could give you a lot of information.
Right, but I would have thought that if there's one place where simulations, hydro simulations, are, give a full description of the physics pretty much is Lyman alpha, and I just don't see much need for going to these phenomenological EFT approaches, which are in some sense unphysical, right? Because the coefficients are unphysical often. So it's not clear to me what is the motivation here. So that's why.
True. So with the emulator, you can capture all the very small scale physics, which is quite cute. So potentially that might be the route to go.
All right. Any other question? If not, let's thank Roger again. All right, so our next speaker is Christoph Jesch, who's talking about mapping distant universe with Lyman break galaxies.
Okay, so I'm going to present how we can map the distance universe with Lyman break galaxies. And basically, all the plots and the figures in my talk are in these papers that we have released 2 weeks or 3 weeks ago. I'm not going to show again the motivation for this physics, but basically what I want to discuss first is the range in terms of redshift. Usually we say that we can go from 2 to 4.5. I think that we can go even further. We can go to 5.5. And basically we have 2 different class of project. We have the project S5, Spec S5 MUST, which is a 6-meter telescope class. And we have other project with 12-meter telescope. But anyway, this means that we are going to have a gain by a factor 10 in the number of modes that we can observe. And here I will use essentially quasars, I mean Lyman break galaxies, LBGs in short, or Lyman alpha emitters, LAE in short. And I will say a few words about the quasars. Okay, just about the target selection of the LBGs is quite simple. You can see this on this spectra. This is a spectra with a redshift 2, and here after you have a spectra with a redshift 3.5 in red. So what you can see, basically what we want to detect is this decrement in the flux in the Lyman alpha forest or in the Lyman beta forest, or even below the Lyman alpha limit. And the principle of the selection in these two colors, G minus R and U minus G, is quite simple. We want to measure this decrement in UV. So this means that we want to measure U minus G, and we have basically a straight line, and we take objects above this straight line, but we have also to consider in red these contaminants, which are the stars. So this explains why we have this shape for the color box. So as I mentioned, we need a U band, so we need a deep U band, and this can be provided by LSST in the south. And we know that with LSST Rubin, we will have the photometry at the time of this new generation, S5. It's not exactly the same for DZ2, but at least for this generation, we will have LSST and a deep U-band for LSST, which will be at the order of 26 in depth, and the footprint will be at the order of 15,000 square degrees. Just to demonstrate that we are able to select this kind of LBGs, we have used DAISY and clouds imaging. Actually, clouds imaging is a very deep imaging in the blue. The depth is at the order of 27, 27.5, and we have used this on two fields, the Cosmos fields and the XMM fields. And really, with this depth, we are able to test the target selections that we will deploy for the S5 projects. There is another approach, which is LAE selection. In a certain sense, at the beginning, it's fully orthogonal. What you want to measure is an excess of color in a very narrow or medium band. And it's what you can see here. You have this color, which is the flux in the narrow band or medium band minus G as a function of the flux in the medium bands. And what we want to color, to select is below this straight line. So in certain sense, it's orthogonal. But we can develop hybrid methods, which will be very useful, for instance, for DZ2. And the idea is to combine the medium bands to create an artificial broadband. And in this case, you can use a traditional dropout selection for the Lyman-Bright galaxies, and you can use the color XX for the selection of the LAEs. So let me show you the results that we get with DAISY. So here it's a stack of several LBG spectra, but it was observed really with DAISY with a 4-meter telescope. And at the end, in our test, we have targeted more than 50,000 objects, and we have observed these targets in two different fields, Cosmos and XMM, as I explained. And we have different exposure times from 2 hours to 5 hours to study how sensitive and what is our efficiency depending on the exposure time. And what's very important in this kind of pilot survey is to have some visual inspection, which is very hard for this kind of spectra. But at the end, we have 2,000 spectra. And with these 2,000 spectra, we were able to build true stable. And with these true stable, we have developed a pipeline, which is based on a two-step approach. First, we are using a CNN to provide the identification of the object, to say, oh, this is a quasar, this is a ELG, oh, this is a LBG. And we have a first estimation of the redshift, and we use this redshift as a prior with a template fitting method, RedWalk, in which we have introduced new templates. And after, we can compute a very precise redshift. And here you have a comparison between the visual inspection and the automated redshift. It works rather well. And at the end, the accuracy that we have on the measurement of the redshift is at the order of 200 kilometers per second. What is exactly what we need for clustering studies. And the fraction of outlier depends on the threshold that you apply with the CNN, but it's at the order, for instance, of 10% for this plot. And here you have the first result, which is a distribution in blue for the redshift that you can compare with the photo Z, and there is a good agreement. And what is more interesting is this plot. This plot is what we call the total efficiency as a function of the photo Z. And what is shown is that above redshift 2.8, our efficiency, this means the number of targets for which we are able to determine a secure redshift is 70%. Below, we have a decrease of this efficiency. And we have tried to explain the reasons, the origin of this decrease. It's difficult to give a final answer, but we have several explanations. First, we know that in this region, we are in the UV region, the SNR per pixel is very low because of the throughput of the instrument. And also, we think that we may have a galaxy evolution. This means that the fraction of Lyman alpha emission is lower for this region. Anyway, at the end, this is the result. This means that if we want to select something with a photo Z between 2.2 and 2.4, the fraction of the efficiency at the end is only 30%. But anyway, above 2.8 is at the order of 70%. We have also measured the bias of this distribution because it's an important ingredient in all the forecasts. And we have measured the bias of the distribution of the LBGs for the two feed, and we found consistent values, which is 3.3, which is also consistent with what we expect from the literature, a value of the bias around 3.5 for this kind of redshift. Finally, we have also used a G dropout selection. A G dropout selection means that you replace the U by G, and you are using instead the I band. Here you expect a distribution between 3.5 and 4.5. It's exactly what we found. And for DAISY, so far, we have efficiency which is rather low. It's at the order of 20% with 2 hours, 35% with 5 hours. But this means that if we extrapolate this number to a 12-meter telescope, we will have an efficiency higher than 50% with 1 hour of exposure time. So here, this is the N of Z that you can get with a 12-meter telescope. So you have the 3 dropouts, the U dropout between 2 and 3.5, the G dropout between 2.5 and 4.5, and finally the R dropout between 4.5 and 5.5 in redshift. Again, to get the efficiency, we are using for 12-meter an exposure time which is below half an hour. For G dropout, we need 1 hour. And finally, for the R dropout, we think that we need at least 2 hours. But we can expect, even with the R dropout, an efficiency at the level of 50%. This is the forecast that we can get with a configuration which is very simple, 40,000 square degree. We have redshift between 2 and 5.5, and the exposure times that I've explained before. The binning is 0.1, and you can see that between 2 and 4, we are almost at the level of the cosmic variance. So you have to compare the red curve and the gray curve here. And we can go up to 5.5 in redshift. So this means that we will have indirect constraints on early dark energy models and exotic models. And this is what we obtain here for F sigma 8. For the FNL, what's important is that we can break the sigma around 1 barrier with only the U and G dropouts. And if we add the R dropouts, there is a gain. We are at the order of 50% on the error. And this is really the reason that I think it's worthwhile to study if we can use the hard dropout with the 6-meter telescope. We really need to study this point. For neutrino masses, of course, it depends on the errors that we have on the optical depth, tau. And if we assume that at the time of S5 generation, we will have a measurement with Lightbird at the level of 0.02, this means that the sensitivity that we will have on the mass of the neutrino mass will be at the order of 15 millielectron volt. So this means that we will have a measurement of the neutrino masses in a standard model better than 4 sigma. And just to finish, because it was presented by Andreu, I think that we can also use those LBGs for tomography with the Lyman alpha forest. But here we will use the Lyman alpha forest of the quasar. We expect between 100 and 200 quasar per square degree. And we can have a good signal to noise ratio. I mean, at the order of between 1 and 2 for at least 500 and even 1,000 line of sight with LBGs. So with that, we are able to do a science of protocluster, but also cosmology with the voids in our 3D maps. So just the conclusions. With this DAISY pilot surveys, we are demonstrated that we are able to target these LBGs, at least for the U and G dropout. We have some estimate of our efficiency, and we have some estimate of the exposure type that we need to get this efficiency. And what we can expect with this S5 generation, we can expect between 8,000 and 10,000 targets per square degree. And we will cover the redshift range between 2 and 5.5. And as I mentioned before, it's worth studying if we can use the hard dropout with the 6-meter telescope. Thank you. Questions? Right.
Hey, thanks, Christophe. So on the R dropouts, you're saying we get something like a factor of 1.5 higher precision on FNL local. What was that your factor? What was the factor increase?
Okay, the gain is from this number, which is around 1 to 0.65. So it's a 50% gain.
50% gain, yeah.
It's not nothing.
So that's.
And let me finish.
So how is that possible? Because you're not doubling your effective volume by expanding from 4.5 to 5.5. So how are you getting that extra precision? And, I mean, I would think that if you this is a volume argument, especially for a 6-meter telescope, I would think you would want to go to a larger area.
The first order is the number of modes, I agree, but you have really to compute the volume. But I think that there is a gain, maybe by a factor 2 of the volume. We have just to do that. It's very simple. As a first order, it's a gain in the volume.
There's also a question of bias and
yeah.
And there's a 1 to Z factor.
But I thought we would be effectively deep, we would be cosmic variance limited between redshift 2 and 4.5. So I wouldn't think the bias would gain you, or does it? I don't.
Here we have considered that the bias is the same, which is difficult to treat because we don't really know the evolution of the bias. Okay, at the first order, it's just a volume effect, I think. You can compute that.
Just to answer this, for multi-tracer methods, there is no sampling variance limit. It's just a shot noise.
I don't think that's being applied to these forecasts. I agree with you, but I don't think that's in these forecasts.
Any other question? Actually, I had a related question on the previous slide, I think. No, one more. This one, yes. I mean, here you have this MP at a fixed bias, but as you go to higher number density, bias should go down. So
that's a point which is very important. Yes, it should go down. That's what we expect. But at a certain point, I think that we have also to measure it because the color burst is not the same. We are not selecting the same objects, so in color, I think. So you can have evolution as a function, of course, of the mass, but also because of the color in your selection.
Right, but I'm just trying to make a point that I think it's impossible to have a bias of 3.5 and number density 10 to minus 3, just from the Halo mass function.
At least for this part, we have measured the bias, is consistent, and after that's true that we can expect a lower bias.
All right. Oh, Julien, you have a question?
That's something we really don't talk about in this conference, that it's going to be extremely hard to measure. We almost we don't talk at all about that in this conference, but it's going to be extremely hard to do those measurements of FNL. With an efficiency of 50%, you will have to understand to correct for that to what precision over what angular separation in order to get the numbers that you quote.
You mean about the correction about the imaging, about the target selection?
Yes, how well
Okay.
are you going to be able to understand the efficiency of your
I agree.
system?
That's another point. I mean, here it's just we are just using a volume bias, and that's all.
Yeah, I know. It's another point, but actually it might be a killer. So, yeah.
No, but we are demonstrating with DAISY that we are able to recover a part of the imaging selection effects. So we have to continue to demonstrate that it works. And another point here, which is very important, is that we expect to have a deeper photometry than what we have now with LSSTs 10 years from now.
Okay, yeah, actually, we can continue this during this conversation. Let's thank Christophe again.
Just share screen.
So if you go back, okay.
Also, I want to hide this panel. Okay. And then use that screen.
All right, so our next talk is by Hengame Bakarian on constraining interacting dark radiation with Lyman alpha.
Hello, everyone. I'm Hengame. I'm a graduate student at Harvard, and this is on a work I've been doing with some folks at BU, Martin and Melissa, who are already here, and Ishwar. We basically use the Lyman alpha data to constrain these models of interacting dark radiation that were originally proposed to alleviate the Hubble tension. I'm going to start by talking about lambda CDM, which is the standard model of our cosmology. The really big success of lambda CDM shows itself when we look at the temperature correlation functions of the CMB. As you can see, this is a very nonlinear, non-trivial function, and the fact that lambda CDM manages to describe this function with only 6 parameters is really a big feat. And the other success of lambda CDM shows itself when we look at the matter power spectrum. And there we have a little bit more of a patchy data set. We have like data from CMB, galaxy clustering, weak lensing, and at the very small scales, we have the Lyman alpha showing up on this plot. Even though lambda CDM is pretty great, like a lot of things that are too good to be true, it's not without its flaws. And a lot of people here in the audience have already heard about the Hubble tension, which is the 5 sigma discrepancy between the direct measurements of the Hubble parameter and the indirect measurements that uses lambda CDM fit to the Planck data set. Another sort of shortcoming of lambda CDM, if I were to describe it, is the overprediction of structure formation as we get to smaller scales and higher K. Representatives of this tension, I would say, is one that a lot of people are familiar with, is the S8 tension. That sort of basically summarizes down to the amplitude that lives around 8 megaparsec scales. And another sort of a similar tension shows up when we look at the Lyman alpha data set, which I'm going to focus on in the next slide. We can sort of think of this is the range of Ks that are basically we're getting the Lyman alpha data set from, but we can sort of think about it as I talk in the next slide as living at around 1 megaparsec scale. The Lyman alpha data set lives at very nonlinear scales, but for the purposes of our work, we don't actually fit to the actual data, but what we use instead is a compressed likelihood of the Lyman alpha data set that summarizes everything to the slope and the amplitude of the matter power spectrum that lives around 1 megaparsec, as I just said. And this is the slope and the amplitude of the linear matter power spectrum, just to emphasize that. And here on the right-hand side, I just plotted the magnitude and the slope of the matter power spectrum in comparison to S8. You can see it here. And I just want to mention that these sort of compressed likelihood actually, there are two measurements of this compressed likelihood, and they are in about 5 sigma tension with the lambda CDM prediction from Planck, and they are in tension with each other. So you might guess that this discrepancy might come from statistics or systematics, but I guess like a very hopeful like model building sort of view towards it would be that lambda CDM is just not the right model to be fit to this set of data. And in order to do that, we have to have a model that actually manages to explore regions of the parameter space that are favored by these likelihoods. Another thing I want to point attention to on this plot is you can see there's, apart from the discrepancy, there's actually a correlation with the measurements of the Hubble, with the predictions of the Hubble value in lambda CDM. And this correlation actually goes in the unfavored direction for us, because if we try to get closer to the regions that are favored by Lyman alpha, we're actually getting smaller values for the Hubble tension. So if you want to have a model that is both happy with the, that's basically alleviating both the Hubble tension and fits the Lyman alpha data set, we want to come up with a model that first suppresses the amplitude of the matter power spectrum at small k, and second of all, fixes this correlation issue for us so that it's not going in the wrong direction anymore. We can start addressing the Hubble tension in these models by changing the physics that we use to extract the Hubble parameter from the CMB dataset. We can do that after recombination, which I'm not going to get into, or we can do that pre-recombination. And if we're building models that are changing the physics pre-recombination, we just like, it's good to remember that the universe is radiation dominated at that point. So adding perhaps some extra dark radiation is a very natural thing to do, because once we cross the matter radiation equality, any sort of extra dark radiation that we added is going to dilute itself away, so we don't have to worry about any late time lingering effects. And the way that injecting this extra dark radiation in the radiation domination era helps with the Hubble tension actually just comes down to this very simple trigonometric formula that relates the angular scale of the sound horizon to the measurements of the Hubble scale and the linear scale of the sound horizon. And the angular scale is pretty much fixed when we look at the CMB data. And adding that extra radiation basically causes a faster expansion in our universe. So it reduces the RS that you're getting from your model. And that leads to you extracting and predicting higher values of the Hubble. Another sort of appeal of injecting this extra dark radiation is that if you decide to couple it to your dark matter at the time, it can also help you suppress structure formation. And that goes in the direction of addressing the tension in the large scale structure sector that we talked about earlier. Now, once we're thinking about these injecting this sort of like dark radiation, there are different types of dark radiation that we can consider. There's always the free streaming dark radiation that you can add, but that turns out to have its own shortcomings. And when you fit it to the CMB data, so you can also consider like self-interacting dark radiation, which addresses some of those shortcomings and actually manages to give a better fit to the CMB. And you can also have more exotic models where in this case, your dark radiation can have two components, and one of them has a mass scale. And by playing around with this mass scale, you can basically choose at what redshift you're deciding to inject this extra and effective into your dark radiation sector. So I'm going to be focusing a lot on these the self-interacting dark radiation model, what we call SIDR, and this fancier exotic one, which we call WZDR. Now, once we are thinking about these like self-interacting or like basically interactions within the dark sector, we can also add an interaction. And as I said earlier, couple this dark radiation to our dark matter. And once dark radiation and dark matter are coupled to each other, the difference that you have compared to the case of a cold dark matter is that now your dark matter is going to experience some extra pressure, and that's going to stop your dark matter from clumping together compared to a cold dark matter case. And this is what is going to help you suppress that structure formation. And the parameter that's we're going to be playing around with to determine the strength of this interaction comes from the momentum transfer rate, or as I said, like basically you can think of it as the strength of the interaction between dark matter and dark radiation. Okay, now we go back to that original plot that I had for Lambda CDM, but now we're looking at the models with this self-interacting dark radiation that's coupled to dark matter, and the fancy stepped fluid that's coupled to dark matter. You can see compared to the Lambda CDM, these models actually are very well within they're actually exploring the regions of the parameter space that the Lyman alpha data favors. And you can see that here, as I tune the interaction, as I increase my interaction strength, I am suppressing more and more structure until I manage to hit the parts of the parameter space that Lyman alpha data favors. Now, I want to emphasize something here. If you look at this relation, this is a very smooth suppression of the matter power spectrum. And if you remember, the compressed likelihood that we're using is extracted from the nonlinear data, assuming a Lambda CDM model. But as long as we have this sort of a smooth suppression compared to Lambda CDM, you can sort of think of these models as extensions from Lambda CDM, because you can pretty much get the same shape of the matter power spectrum by messing around with like AS or NS, like within Lambda CDM. So it should be pretty reliable to still use it with the compressed likelihood of Lyman alpha. And finally, you can see that in these models, the thing that happens that's important is that sort of negative correlation that you have with the values of H0 actually goes away. So now you have opened up this extra direction in your parameter space that allows you to start addressing the H0 tension at the same time without messing up your fit to the Lyman alpha. These are the full runs for the WZDR, the step fluid model. You can compare it to the posteriors for H0. You can see this fits well within the posteriors for H0, S8, and here the Lyman alpha likelihood. We have similar plots for the SIDR or the self-interacting dark radiation model, and you can draw similar conclusions. And for those of you who are interested more in the a more quantitative measure of how well these models are doing, you can look at the tension table here. Lambda CDM is both in like roughly 5 sigma tension with both the Lyman alpha data and H0, as I mentioned earlier. And SIDR plus and WZDR plus models managed to be, I mean, they're not in tension with the Lyman alpha data because they're just like crossing that region of the parameter space. And they managed to cut the H0 tension basically in half. So just to summarize, Lambda CDM is a very good model of our cosmology, but it's not without its flaws. It can have like, we're dealing with tensions like H0 and large scale structure, and interacting dark radiation models are a very natural way to address that. And we're hoping that with future data from DESI, we can basically hone in on this Lyman alpha data and figure out what's going on with the discrepancies of within the data sets, and hopefully find better fits in to both models.
Questions?
Yeah, thanks for the nice talk. I think you were mostly discussing Hubble tension. Do you also have some comments about the SA tension, since you mentioned that in the last slide?
Right, yeah. I don't have the quantitative measures for it, but these models also, like, because of the same suppression that I showed plots for, you also manage to alleviate the SA tension.
I see. From what sigma to?
I think from like, I mean, so the data sets that we used here, it was already like not in very strong tension because we were also using like the full shape data set and everything. So we, the S8 that we started with, I think had like a 1.7 sigma tension to begin with. And I think it reduced that to, I I don't quite remember, but like 1.2 or something like that. I don't know, maybe.
I see. Thanks.
But your essay didn't change much, no?
No, it's not because it didn't have, it wasn't intention to begin with, really. Like it was like a 1.7.
Right, but I guess your essay goes, sorry, is there?
So S8 is already included in the D data set here. So it was in our baseline data set.
So
The
you don't
S8
have,
prior was already there.
sorry, these plots, these fits are with?
With S8 included.
No, I mean, what data goes into this?
In the D has S8 and CMB and full shape data set.
So full shape of Lyman alpha and CMB Planck?
Not the Lyman alpha full shape, no. The full shape from EBOS. The DR. Yeah.
So that's what goes into this.
That's what goes into D, correct.
And
S8 is also like the S8.
And CMB lensing is in it here or not?
Yes, CMB lensing included.
Yeah, correct. Hi. So I just wanted to repeat a message I gave in my talk that this Lyman alpha data is not the BEO measurements of Lyman alpha, right? Those are like the small scales measurements. Correct. And if I understand it, it comes from a paper from which a plot was read off and a Gaussian likelihood was approximated to the plot because the likelihood is not public. So I want to, it's not a criticism to your work, it's a criticism to the likelihood should be public. So I think we should always ask everyone who works on anything related to observational cosmology, make your data, your likelihood public, otherwise people will read from your plots, contours, and then there will be 5 sigma tensions that probably, if the likelihood was public, that tension would not be as strong. So yeah, I would like to encourage everyone to make the likelihood public.
Any other question, comment? If not, let's think again. All right, so I guess we have some time for discussion. And instead of calling people out here, let's just, I have a few set of questions that I prepared, and maybe we can just discuss them. Let's start with MUST. So the first talk was about MUST survey, which is a northern version of MegaMapper, as was described. And so the question is, I mean, do people have, how do people think about it, right? Is imaging, for example, a concern? Because it doesn't have Rubin overlap so much, things like that. So if anybody wants to answer, yeah. No.
Yeah, this is a very good point. Actually, I would like to use this time to share some of our concerns on the imaging survey, because this is really critical. Yeah, so basically, currently our best chance is to rely on the Chinese Space Station telescope data, so CSST data, because it's in the space and there will be good U-band imaging. So hopefully, if it's launched in time, then hopefully we will have access to this data for our LBT selection. And also maybe the Euclid data will be also partially public by that time, and the infrared data could also help for our target selection. Yeah.
And as a follow-up question, would, I mean, what Christoph was talking about, where are you? Would, you know, for you also these data be useful? Euclid and I guess this Chinese mission that I don't know much about.
Data will be. Yeah, there will be public releases, but yeah, I also don't know when and how they will be released.
For sure, that's very important to have a DPU band.
Yeah, I think so. The design depths in basically UG, RIZ, wideband, they're trying to reach beyond 25 magnitude. The U-band, yeah. So the honest answer is a bit uncertain, because right now they decided to switch to domestic CCD. So we don't. On the paper, it looks good enough, but we haven't built the camera yet. But the design depths right now, the 5 sigma pointer detection limit is still definitely beyond 25.5 magnitude. So that's the, yeah. The point is that CSIT is really, it's a survey telescope. So it'll give you basically a full sky coverage in all those bands. Yeah, and right now I think the launch date is somewhere between 2026 and 2027.
Any other question or comment about MUST?
I guess I'm wondering, in a world where both MUST and SpecS5 exist, how much do we want them to be completely independently operated to cross-check each other versus how much do we want to coordinate, targets, redshifts, samples, et cetera? Discuss.
Yeah. My answer is that we want to be as open as possible. So I definitely think the cross-validation will be super important for cosmology in the next decade. But it's subject to political issues, which we don't have control. Yeah.
Okay. So maybe first from the Chinese side. So I think again some people here know the history. So originally the project started with a private donation from Chinese rich people in China. Now they invest in science now. Originally really want to build a mega mapper together. So that's the real story. And then that didn't work. And we saw the mega mappers going to the south. So why not we build one in the north in China? So that's the real story. And right now, in terms of how I have very little understanding about the U.S. policy. All I can say is that our project is happening. So it's not. We did successfully. So I think I mentioned and this in the other occasions that what we lack in experience and expertise, we compensate with money. Basically, we have successfully raised about $140 million. So that's not the money we are going to get. That's the amount of money we have spent already. The contract has been signed, and it's an enormous pressure on many of us. And I can't remember the last time I had a good night's sleep. But but we are building it. We are building it. We understand the challenges, but we are building it. So it's very hard to predict what will happen in terms of the China-US relation or the politics situations. But as Cheng said, we are as open as possible. So maybe this is not the best occasion to say this, but our science, basically I'm writing the science collaboration policy right now. So I want to make a really, really big discount for everyone who want to join us. Basically, unlike DESI, we don't want money. We want your experience and expertise, so that we can really work on it.
Yeah. All right. Any other comment on MUST? Otherwise, let's move on. Okay, let's move on. I guess second and third talk were about Lyman alpha, and I guess we did not see the constraints on running of the spectral index, but they seem they should be a factor of few better than whatever DESI is promising, and therefore they should get into the regime of something that is guaranteed detection, perhaps, one of those known unknowns. And so the question is, should that be one of the key science goals for SpecS5? Any comments?
Maybe a question as opposed to a comment is so I guess the Lyman alpha forest is really the small scale information. Is there anything from the clustering directly from the discrete tracers that gets us competitive measurements of the running, or are we just cutting off at too large a scale to be relevant? I guess my question is, how does the direct tracer technique complement the Lyman alpha forest technique, given that we are claiming to go to smaller scales with these?
So and
What scale are you cutting them at?
Well,
So even going to 0.2 assuming linear,
thinking,
right?
I think.
In that paper, it wasn't going to 0.2 assuming linear theory, and even then it was not helping much.
Quite that simple, but yeah, it just didn't.
yeah, one way to think about it, CMB goes to K of 0.1, so it's it's a strong overlap, right? And then Lyman alpha forest gives you another order of magnitude in scale, another factor of 10. Okay, so I guess a related question is, however, so I think I got a bit confused about the last talk. Was the question about Lyman alpha that Lyman alpha has a suppressional power, and which can be explained either by running of the spectral index or by some of these models? Was that, where is the speaker? Oh yeah. So we've seen, I guess, from previous Lyman alpha forest analysis, some evidence for a running of the spectral index, maybe shallow NS. Is this the same effect that you were describing with the likelihood that I guess it's not public or something?
Not about the likelihood, but yeah, there's simulations that like go along with the models of like letting the spectral index run, as opposed to just the Lambda CDM like mock simulation. And this would go along the lines of what I said towards the end, which was as long as you have like smooth suppressions of Lambda CDM, like this sort of extrapolation from the nonlinear to the linear, like compressed likelihood should be reliable.
Yeah, but I just want trying to get the zero order effect. Those the 5 sigma you were saying there's a 5 sigma discrepancy with Lambda CDM, is that right?
Correct.
That's for assuming alpha, the running is 0, right?
Correct.
If you have running, then you can explain that, but you need a very large running. Is that correct?
Well, the paper with the running, I believe so. I do not remember exactly their like how large their running was, or exactly like how they managed to short it down. But yeah.
Right. Okay.
You should be
So again, maybe we should add dark radiation models to the science case, I guess. I don't know.
Yeah, just adding to this, so it's running, typically you expect it to be small from inflation and not big enough to explain the kind of suppression that this Lyman alpha data was showing. But with models in which you couple dark radiation to dark matter, it's very easy to produce something that looks like running of the spectral index. And with the very large, there's a free parameter that allows you to dial how much running you want. And so I would say it's important to go for measuring the running, and the target is not only the tiny running that you expect from inflation.
Right. And so I guess the related question maybe is how robust is this evidence of running from Lyman alpha? Because I've seen different emulators giving different results. Anybody wants to comment on that? Christoph? Yeah.
I have a comment because I don't really know what's likelihood is used for this kind of measurement, because I wrote the Lyman alpha paper, so I want to know what likelihood you use for it.
Just to add, yeah, in terms of the robustness, also commenting on your EFT, let's say, critique in this regard. So we reanalyzed the Lyman alpha data, 1D power spectrum with EFT, and we found no evidence for running. So that means that maybe there is some, extension of the standard emulators that is needed actually to explain the suppression.
Right, but my understanding of Simon Bird's emulator is also this, evidence for running in their analysis. So there seems to be some controversy here, I guess. Different emulators seem to give different results.
So I have not been involved in any of these analyses either. I only do the BAO until now. But I mean, again, like, you know, the livelihood from Simeon is not, the Simeon bird is not yet public. The livelihood from Christophe and collaborators is not yet public. I don't know what was the other contour that I saw in that talk. We just need like a proper code comparison, you know, can we reproduce your results? Can we compare, you know, livelihood evaluations of the same model or things like this? Without that, I think it's very difficult to tell what's going on.
Okay, any other comments on this subject? All right, I have one more thing to discuss. Yes. Okay, so I guess maybe maybe we want to discuss what Julien was worried about. I think you were worried about angular systematics. Is that right?
So I haven't worked personally on the analysis, but I've seen some studies about scale-dependent bias measured with quasars in eBOS, and also I am aware of the work that is going on in DAISY. And my perception is that those analyses are very difficult, and that we have to face that problem. On the data side, it will be not just about getting better spectrographs, but also designing ways to reduce systematics on large scales. I don't know exactly how to do it. And maybe on the theory side is designing observables that are less prone to those imaging systematics, like removing the transverse scales in some way, or if you're working on three-point function, finding ways to be less sensitive to systematics. And I'm surprised that we didn't discuss that much in that meeting.
Well, this is a theory workshop after all.
Actually, that's a very important point. And for instance, for DAISY, we are starting to work on this correction due to the imaging with machine learning techniques. And it's just the beginning, but it works with MOX. So this means that at the time of S5, I think that we have developed the tools to be able to recover all the effect due to the imaging. But that's true. At the time of DAISY, is the main systematic now.
Okay, so I just want to add one thing, which is that 3D surveys, spectroscopic surveys, actually are best suited to remove the angular clustering systematics without actually losing much information. So this should be the strength, actually, of spectroscopic surveys such as SPEC-S5, not a deficit, right? So imaging surveys have a lot harder time removing, because in imaging, everything is angular, right? Whereas in 3D surveys, angular part of the modes is actually negligible compared to the total number of modes.
I'll just say it is important, though, to know what the important things to measure are here. So like the running, you know, if we look at DESI was designed around measuring the acoustic peak. That's what it was designed for. Instrument, survey ops, everything like that. These other measures like FNL running, it could fundamentally affect the design of both the instrument and how the data is taken. So it's, you know, you can just like plug in the numbers and say, okay, in principle, if everything's understood, how well can we do? But it's not going to work for these really challenging measurements, I think, unless we design for it. Yeah, so SphereX, for example, is a project where they're designing around these for the existing ground-based redshift surveys. We have not yet.
Any other comment? Well, if not, we can stop here and let's have lunch. Thanks, everybody.